good morning. I'm Irene Diaz, a software engineer at Red Hat, and this is my colleague, Sarita.
Hello everyone, good morning, and thank you for getting up early in the morning to come for our presentation. And today we are going to talk about two onboarding options, that one with Ignition and other being, one being FDO and other being Ignition for IoT devices.
So this is today's agenda. We are going to discuss what is onboarding in broad terms. Then we are going to present to you what are the options that Fedora IoT has for onboarding, as well as future steps and what is coming up for Fedora. So what is device onboarding? Why do we care, and so on? So device onboarding happens after we make an image, provision it, and then we have to give the devices all the configurations and secrets that they need in order to perform its final need. During this onboarding process, we also hope to get a connection from the device to the final IoT platform. The platform is what the device needs in order to get updates and some other software and so on. This whole process, of course, needs to be secure in each of the steps, and there shouldn't be a need for human intervention, so the whole process should be hands-off. So if you can imagine, if we are trying to onboard 1,000 devices in the middle of a mountain, an engineer cannot be bothered to go to the onboarding site. We simply need someone to ship the devices over there, power them on, and everything else should be automatic, secure, and no need for human intervention. Fedora has two different options in order to do this, so Sarita is going to give an overview about them.
Let's get a brief introduction to these two options. What is FDO? It's basically FIDO device onboarding. Protocol? It's an open industry standard protocol developed by FIDO Alliance. FIDO Alliance is basically formed by a couple of tech leading companies such as ARM, Intel, Google, and many to name. A little bit of history to FDO. FDO was initially known as SDO, which is Secure Device Onboarding, developed by Intel, and later it was contributed to FIDO Alliance to become FDO with enhancements. Whereas Ignition it's a part of CoreOS ecosystem, which is internally developed by in-house in Red Hat and maintained by a group called CoreOS Working Group. The basic difference between the two options, I think it's in their infrastructure. Because of the distributed nature of FDO, it requires a proper complex infrastructure, maybe a server-side and the client-side implementations, which we will see in details later. And comparatively, I would say Ignition has a simpler infrastructure, which basically revolves around one configuration file. Although this configuration file, it can be linked to other configuration files, which you can run which will be merged at the runtime. So. That's the basic difference, but we'll see the more details as we go ahead.
So how do FDO and Ignition fit with Fedora IoT? So in order to make a Fedora IoT image, you would be using Image Builder. There have been previous talks in this conference about what is Osbuild Composer, Image Builder, and so on. So if you haven't seen them, I would recommend you to check those other talks. So you would use a blueprint in order to make a Fedora IoT simplified installer or a raw image, then use Image Builder to produce that image, and then once the image has been provisioned, you would use either FDO or Ignition, probably both at the same time, and at first boot, the devices would be onboarded. And Sarita is going to explain a little bit more about Ignition, about FDO.
Yes. So let's see some of the key features of FDO. The whole idea of FDO, it works around providing maximum security during the end-to-end onboarding process. So, of course, the first thing comes is no manual intervention. There comes zero touch. Where are the maximum possibilities that security threats can be there? FDO works by the principle of establishing a chain of trust. To explain this a little bit more, I would like to go to the next slide, where we have the whole, this is the FDO protocol, which Irene is going to tell us about in a bit, about the flow and how it works. But a few of the concepts to explain the chain of trust. So FDO can be seen or divided into two phases. One happens at the device manufacturing site, and the other, it happens at the onboarding site. So at these two phases, they can be in different timelines. So there has to be security in terms of its ownership, which is provided at each step. The ownership of the device, it can change during the whole time, a number of times. So okay. Apart from this, one of the features that's most spoken about FDO is late binding, which solves a lot of problems related to onboarding in the industry. So what is late binding is, so when the device is manufactured, device does not know that which platform it is going to get onboarded, or the configuration that it is going to onboarded with. This can be decided at later stages when the device actually goes to the on-site, and that's when this feature allows flexibility in terms of device management, which is very useful. And yeah, that's the feature. And apart from this, FDO has other features such as reliability in terms of if there are a number of devices, every time FDO works, it works the same way for all the devices. And even though the protocol is pretty complex for the end user, it's very simple to use. Even a semi-skilled worker can power on the device at the onboarding site and doesn't need to know what happens inside. It is platform independent and cost saving, I would say. I mean, the infrastructure does take, is expensive since it's complex and it has hardware, software requirements, but it's a one-time job, and it saves a lot of manual processes, and even simplifies the errors that could possibly happen when traditional or manual onboarding is there. So yeah, let's see.
So now FDO in a little more of detail. As Sarita said, there are two places where the whole onboarding process happens. On the left side of this slide, you see the device initialization part, which happens at the manufacturing site, and then we have the on-site onboarding part. So during device initialization, there are two entities that are important. First of all, the device, and then the manufacturing server. The device would contact the manufacturing server in order to get a GUID, and two different, I guess, documents would be generated. One are the device credentials, which will be hosted in the device, and those device credentials tell the device where it would find the rendezvous server later on in the process, which is on the onboarding side. The manufacturing server would get an ownership voucher. This ownership voucher is a cryptographic document, and using that document, which is a 509X certificate, the FDO protocol allows you to verify that you are the owner of the device at a current point in time. So in this point in time, the owner of the device is the manufacturing server. The onboarding is still going on, so the device would be moved to the onboarding site, and meanwhile, the manufacturing server would transfer this ownership voucher to the owner onboarding server, so that right now, at this point in time, the owner of the device would be the owner onboarding server. As you can see in these slides, the communication starts. The device contacts the manufacturing server. That is what the arrow means, but the connections, are answered and so on. So the device reaches the final point, and then the owner onboarding server would transfer this ownership voucher to the rendezvous server, and in the rendezvous server, we would have a mapping from device GUID to an IP, and that IP is what the device will later on use to contact the owner. So the device finally reaches its final step, and it would use the device credentials in order to find where its rendezvous server is. So it would contact the rendezvous server. The rendezvous server would check if that GUID makes sense to him, and if so, it will tell the device where its owner is. Then the device will contact the owner. They would establish a chain of trust based on the keys that the device has in its device credentials and the keys that the owner has in the ownership voucher. The owner would transfer some keys to the Service Info API server, and the device would then contact the Service Info API server in order to do these final onboarding steps, which is where the device would get all the configurations and keys that it needs in order to work. So how does it fit with the, how do we do this? So as we said before, in order to build a Fedora IoT image, you will need a blueprint. In order to use FDO, you need a simplified installer blueprint. And the only thing that you need to add to this configuration, apart from any other configuration that you might need, is a customization.fdo, part where you would place what is the URL to your manufacturing servers, because as we said before, the only thing that the device needs is just an IP to get to the manufacturing server, and everything else would be automatic from that point on. So we would use image builder. If you're using the command line, you would run composer CLI, compose start OR3, and then the name of your blueprint, which is a TOML file. Then you would select the type of image that you need, any other further parameters. Since Fedora IoT is an OS3-based operating system, which means that it has an immutable file system, you would need a commit in order to fetch the file system and so on. So you would use that, and then the image builder would spit a Fedora IoT simplified installer image, which is an ISO. You would provision the device, it will boot, and the whole process that we saw in the previous slide would happen, and the device would know what to do and so on. So, but I mean, we are onboarding the device. How do I get the configuration and so on? The FDO standard has a non-normative part, which are the service info modules. Each service info module is a configuration, module where you can put some atomic instructions, and it works with a key value protocol. So in this slide, you can see that we have a couple of configuration things. This is a YAML file. So we can, for instance, establish an initial user. As you see there, I'm creating a user. I'm giving it a password and some SSH keys. We can also copy files from the Service Info API server to the final device. We can run some commands. We can establish disk encryption in a given disk level, and we can also specify if we want that the device wants to be rebooted after the onboarding process has happened or not. You have an URL over there where you can see which are the FSIMs that the FDO Alliance is working on. Red Hat has a couple which haven't been published there, but we are working towards making them part of the standard. And if you are interested, you can go to Fedora IoT FIDO Device on Board RS, because our implementation is in Rust, in order to contribute or find any more information. And now with Ignition.
So let's see some of the features that what is Ignition, what it can do, and how does it work. Ignition can be described as the first boot configuration tool, although it can be used for provisioning purposes. It basically runs in the initram FS at the first boot. The things that you can do with Ignition involves things such as configuring users, disk manipulations, which you can create partitions, and enabling the systemd services. All of these features, they are supported by CoreOS, but Fedora IoT only supports a part of Ignition, so not all the features that you can do with Fedora IoT. We'll see in details what Fedora IoT can perform too. And Ignition's configuration file, basically it's a JSON document which can be embedded inside the ISO, or it can be kept at a remote location where it can be fetched during the onboarding process. Ignition follows a declarative pattern. That means Ignition knows what stage it is going to be rather than how to do those things. So for example, if it's going to get some disk manipulations done, it knows that it has to partition the disk or what to do, but the how to do part, it gets it done by the underlying OS tools and utilities. So Ignition doesn't have to worry about how to do part. The nature of Ignition, it promotes immutable infrastructure, meaning that the configurations once provisioned or after the first boot cannot be changed. If user needs to do some changes in the configuration, reprovisioning has to be done. This part is a bit expensive in terms of reprovisioning compared to FDO. If after updating configurations at runtime, new configurations can also be applied. There is no need of reprovisioning the device. Also, the automatic configurations are deleted once successful provisioning is done from the VM metadata, which is useful because the sensitive information is not accessible once the device is provisioned. It does support HTTPS and config verification. That's a useful tool too. So yeah, we'll see the next thing.
So how would you configure Ignition in order for a device to be onboarded? As Sarita said, you simply need a JSON configuration file. The current version is 3.4.0. And as we said before, in Fedora IoT, we don't support all the features that Ignition has. In our case, we enable file links and directories creation. We also can create systemd units, users and groups, as well as the other Ignition metadata configurations, such as retrieving a remote file and so on. As you see, there is a JSON file, and this might cause a problem because, as you know, JSON files are not human-friendly. So in order to avoid using JSON files, you have butane. So butane is a transpiler, which is a source-to-source compiler. Butane would take a butane configuration file written in YAML, which is more human-friendly, and then you would use the butane transpiler in order to get the JSON configuration file. And why would we do that? Because while we are transpiling one configuration file to another, we would get warnings if there are any errors, and we also check based on the variant that we are defining over there. I don't know if you can see it, but we are using the RHEL4H variant. If the options that we are given to the butane configuration file are supported by the variant that we want. And yeah, currently the RHEL4H variant is on version 1.10, and we are targeting Ignition 3.3.0. Yeah. So some examples, if everything goes well, you would run Ignition as shown in the first example, and butane would spit a JSON Ignition configuration file. If something goes wrong, for instance, in the second example, I've forgotten to establish an install section in the unit, so butane would tell me, hey, you've got an error there. And if I'm using something that is not supported altogether, in the bottom example, you would see that butane would simply give an error saying that, hey, the file system configurations are not enabled for this variant that you are using. So how would you use butane in order to onboard a device? You have two different options. As Sarita said before, you can either copy the whole JSON file into a section in the image builder blueprint, but instead of using JSON, you would have to transform it to base64, and then if you want to do that, you would only have the option to produce a simplified installer. So you would simply call Composer CLI, choose the image type that you want, for instance, the IoT simplified installer in this case, and then you would get the image. The other options that you have is to specify, as Sarita said before, a remote URL where the ignition configuration file would be fetched at first boot. So if you choose to do that, you can either produce a simplified installer, which is an ISO, or a raw image, which is a compressed raw image. In the case of the raw image, you would run the command that is there, and then you would have the image. In both cases, you would have to provision the device, and then at first boot, ignition would work, and the device would get onboarded.
So after seeing FDO and ignition, you must be wondering which one to go for, which is the option. But to be honest, it's not a one-to-one comparison. It's rather two options that you can choose based on the project requirements, what security features are to be used in the project, and of course the infrastructure based on the differences between the two options. So it's up to the requirements of the project. And yes, the combination of the both can also be used together. For example, some of the features or some of the things that you can do with FDO and ignition, or you can creating the user part disk manipulation or others, they can be kept for ignition, and the rest of the protocol stays with FDO. So some of the future enhancements that are coming with FDO, one of them being the service info per device feature. Irina earlier explained about the service info modules that we have for FDO. Currently, what happens is all the devices get onboarded with the same configuration file. We call it the base or the default configuration. But with this feature, it will be possible for the user to onboard different devices with different settings if they want device-specific configuration. For example, for SSH key, we have started with that, and if the user is not doesn't want the device-specific one, it still has the option to get onboarded with the default ones. Another thing is that we are trying to move to database storage. Currently, what we have is all the files, configuration file, which is ownership vouchers, and the other configuration files are being stored at the file system, which is really not feasible when considering a number of devices. So database will be a good option. We are working on that. One of the things that we are trying to do is moving from Warp to Axum. Warp is a web framework that we use in FDO, but it does not comply to FIPS. FIPS is basically a cryptographic standard that we use, and Warp internally uses RustDLS, which uses ring. That ring crate does not comply with FIPS, so we are moving to Axum. That's it. And yeah.
And we are missing a bit on the left side of the slides, but forget us. This is related to the future of Ignition. So Ignition is developed by the Koreos team. As you saw, we don't support everything that Ignition does. So we are working towards enabling file system customizations during the onboarding process, because right now you would do that in the image building process, and we have a static partition table, so you cannot change that unless you change the code in OS Build Composer. So yeah, all that you have been seeing right now, it will be coming for Fedora 38 as soon as we get back from this conference. That is the soonest part, yeah, but it would definitely be for Fedora 39, and yeah, that's all, and we'll have to take your questions now if you want.
And thank you,
yeah,
everyone, for listening.
That's all. No questions? Fantastic. No questions. Thank you.
We have one
Oh,
question.
oh, yeah. Go.
Say this is our
So, they. So we've been asked where can we get those documentation or information. So
it's available
where?
on our
So,
repository.
but I think that he's asking where would I configure this? Am I right? Okay.
Yeah,
We
but-
do have our documentation in the link that I showed you in the next slide. There is a file which is called the how-to. You have examples over there in order to know how to configure this. And if you are interested in how the protocol works for our specific FVO FSIMs, because some of them are not part of the standard, under the same repo, there is a docs folder where you have docs FSIMs and you have the specification over there. If you are looking for the FSIMs that are going to be part of the standard, which are the ones about the file copying, the commands, and some other one that I'm forgetting about, those things are in the FIDO Alliance FSIM repo in GitHub. Does that answer? Yeah.
So it's each implementation to decide which FSIMs
Yes. Yes. Each FSIM has a set of configuration things that you need to configure. It's not the same to create a user to create a file. So for users, you have can I set a password? Can I set a SH key? Whereas with files, you have the options to set permissions, and yeah, that is the difference. Each FSIM has its own configuration parameters and so on. Yeah. Okay. Okay. Thank you. Okay, another one. So we've been asked whether we.
For ignition.
Yeah. So. Let me. Let me check if I've understood. You are asking whether we have thought about signing the ignition configuration file so that we know that the device would get the configuration file that it needs. We haven't thought about it to the best of my knowledge, so we'll take up that with the team and with the Koreos.
We'll come back to you.
Yeah, and we'll tell you when we have the opportunity. Okay. Are we good? Okay. Thank you.
So, hello everyone. I welcome you on the automotive panel discussion. My name is Martin Peřina and I'm working as a manager in the automotive part of our organization. And today I would like to introduce you my colleagues who I'm working with. So here we have like Pierre-Yves Chibon, he's principal software engineer and the product owner for the Container on Wheels team. I have Rachel Sibley, who is senior principal QE engineer. He's working as a QE automotive lead for the automotive effort. And also we have Daniel Walsh, senior distinguished engineer and the lead architect for the containers runtime platform in Red Hat. So before we will get some kind of our question, of course, we will give talk to you. But at the beginning, let me pass the microphone and my colleague will tell you what they are working on currently.
Good morning, everyone. So I'm Pierre-Yves Chibon, also known as Pingu, more known as Pingu normally. I'm in the, as Martin said, I'm the product owner for the Containers on Wheels teams, which also stands for the COW team, which gives us the opportunity of doing a bunch of bad pun jokes. The team has been created about a year and a half, and we still keep container moving and doing demo every week. So yeah, we're pretty good with bad pun jokes. The responsibility of the team is to look at everything that has to do with running containers in the cars. What are the challenges? How do we run them? How do we manage them? What are the challenges associated with that? So it's a pretty interesting area, and I have a talk about it at 2, I believe, this afternoon in this room to talk about IRTA, and we'll go into more details into that here.
Hi, good morning. I'm Rachel Sibley. I'm the QE technical lead for the in-vehicle operating system in automotive. I'm also the product owner for testing enablement team, and our goal is to migrate existing RHEL tests that relate to the safety scope and run them in an automotive environment. So, I have a talk later on if you want to learn more about that in functional safety and what that means. And it's at 4:15 today in this room.
Yeah, by the way, this microphone does nothing other than for the thing, so everybody's thinking. So we're going to try to talk loud. So my job, 9 months ago, I moved into the Rivos team. I consider myself, my main job is to get containers running everywhere inside of Red Hat. That's my sort of my focus. And when it comes to automotive, I'm looking at how we can use containers in the car, how we use the technology to satisfy a lot of the requirements for us to get approved as an operating system that can run inside of a moving vehicle.
Okay, so Dan, so I will ask a question for you, because like we have published several blogs in the Red Hat blog, and one of the most, let's say, controversial or most visible thing was that we don't believe that the Kubernetes is good to be running in a car. So Dan, could you please explain?
Start with the easy question.
Yeah. So we'll start out by saying I love Kubernetes. I want OpenShift to be successful, and Kubernetes has some key issues. When we talk about putting, the reason we bring up Kubernetes in a car is most of the automakers, you know, that's sort of the first thing out of their mouth is we want to get into this cloud native world, and you know, this whole buy into Kubernetes, and there are going to be multiple computers in a car, so why not just use Kubernetes to move, you know, different containerized workloads around in the vehicle? Well, we're going to be talking. By the way, I didn't mention I have container BOF. I think at 2 o'clock this afternoon. Same time. Yeah, we're competing, so if I get more numbers than him, yeah. You know that, so you know what you think. Mine is just going to be general, you know, similar to this, just general questions about containers, and I'll be potentially show some cool stuff. But and then tomorrow at 2 o'clock, 2:30, I'm doing a talk, containers on wheels, containers in cars. So it's to be I'll show a lot of the technologies and talk about it. But IRTA is one of the key ones. Anyways, going back to Kubernetes in a car. So when you're driving a car, one of the key things in any type of moving vehicle is what they call functional safety. So functional safety means basically we want to make sure that the you don't do anything to injure someone with a moving vehicle. So it's somewhat similar to security in that you want to make sure that the system works correctly. But in functional safety, we want to make sure, for instance, you might have an app that's, let's say, applying the brakes, and then you have another app that is running Netflix. Well, you want to make sure the Netflix app is not like dominating in such a way that the brake app can't fire off. In the world of Kubernetes, so basically when you want to have an app execute, that app has to execute, okay, so to be functionally safe. In Kubernetes, they have the concept of eventual consistency, right? So you want to eventually your app to come up and or eventually the environment to be up and running. So obviously that is not the same thing as the app has to be up and running. So we can't use Kubernetes and orchestrator. The other thing is trying to get to functional safety, you have to really look into the code, really examine the code, and explain how the code always works on time. When you get into multi-threaded applications that are written totally in something like Golang, it becomes a lot more difficult. So lastly, Kubernetes applies a heavy workload. So in a Kubernetes environment, there's always a lot going on, right? There's a heavy the kubelet, cryo, they're always doing stuff. So they're always using CPUs, they're always performing stuff. So there's a lot of reasons not to use Kubernetes in a car. And for our low overhead orchestration is Herte, which is what he'll be talking about this afternoon. And I'll be talking about a little bit in mine tomorrow.
Thanks, Dan. So as you mentioned, the functional safety is one of the biggest challenge or the biggest problem that we are trying to solve within the automotive effort. So Rachel, could you please talk about, like, how do we handle and how do we test functional safety?
Easy. Oh, okay.
She's going to make it happen.
No pressure. So for testing the in-vehicle operating system, we need to, functional safety or FUSA requires 100% requirements test coverage. So that can be a bit challenging, especially the way we inherently do it with RHEL-QE. We're not designing tests 100% functionally testing an API, for example. We take a lot of what's upstream, we rerun it. So part of this is running the tests against our requirements, which are the APIs. Running them, identifying where are our gaps. We use code coverage analysis, GCov, to assist us with that. Developing new tests to ensure that we have that 100% coverage. So a lot of what we're doing with testing is we want to leverage existing tests from RHEL. We don't want to fork their tests or have duplication there. So we're rerunning all of the existing RHEL tests and then adding new tests for any of the gaps that we're finding. And a lot of these, of course, are tailored around the safety scope. And we're adapting them to an automotive environment because the tests weren't designed to run in an OS tree environment. They're designed to run against an RPM traditional compose. So there's some tweaks or changes to the test to get them to run in OS tree, and then migrating them to an updated test framework, depending on where we're running them. So yeah, for testing, it's definitely quite challenging to also establish the traceability. We need to have requirements down to the test cases, the executed runs, the logs, the failures. Every failure needs to be linked to an existing issue. All of this needs to be traceable. We have to have the evidence. We have to have retention policies in place. So we have a lot of work to do.
I just want to point out there's a key word that she mentioned multiple times there, evidence. So to me, functional safety means eventually if a vehicle causes an accident or a machine causes an accident and you go in front of a court of law, you have to have evidence that you did everything to make the system as functionally safe as possible. So that's, so that's really what we're trying to do. This will be the first time Linux operating system has ever achieved functionally safe, to describe Linux in terms of being as safe as possible, right? Doesn't mean accidents are not going to happen, but what eventually you might have to get in a court of law to prove that we did everything possible or our partners did everything possible, so to prevent an accident, right?
Yeah. To follow up on that a little bit, one of the examples I like to take is, you certify an API, and that API can be something as simple as, open a file and write content to it. And the idea of the functional safety is to make sure to guarantee that, if you use that function, what it will do is open a file and put content into it. If there are very specific use cases, there are very specific conditions under which, if I give it a 42K buffer frame and I'm pointing to a very specific place in the file system, under these conditions, the function does not behave as it should, that's a problem. That function is no longer functionally safe. So it's going a lot through the code, examining it, and ensuring that it behaves the way it does. That doesn't mean that the way you can't use the function to actually do something bad, but it means that, it's the example I do is you have a gun, you shoot yourself in the foot. The gun has worked the way it's supposed to be. You pull the trigger, it fired the bullet. The fact that you are aiming it at your foot is your responsibility. The gun did what it did. So the function to open a file and write content to it does what it did. If you use that function to mess with the kernel parameter that landed with a crash of the compute unit that triggered the accident, then the function is what it was supposed to do. The fact that you used it wrong is your responsibility. And a lot of FUSA has to do with this. It's, where does the responsibility lay, and can we track that responsibility? So it's a lot going through all the codes. It's lots of going through all the test cases, and that's why the test cases are important, and the traceability of them are very important, because they are the proof, they are the evidence that the function does what it's supposed to be doing. And some functions are very easy. Open a file, write a file. Some functions, sorting functions, for example, becomes a lot more challenging. And how do we handle exceptions? How do we handle the edge cases? And all of these are becoming back to what Rachel was saying. Testing is important there.
Thank you. As you all said, the functional safety is one of the core problems that we are trying to solve, and that also comes with where the Linux can move on, right? It's kind of very well established on the computers and servers. It's most probably also very well established in the edge devices. Now we are trying to get the Linux to the cars, which is completely new level regarding this functional safety. So Pierre, do you think there are kind of other categories where we could get, or other areas when after we will get into the cars, this work will not be specific only to cars, but we can expand?
From discussions we've had recently, there is definitely an interest in what we're doing. There is the entire automotive industry is curious of what we can do and what we can offer with it. The idea about being able to update systems, being able to have a life cycle, a single software stack that is applicable, that is maintainable across multiple generations of cars is something that is very appealing. In the same way that, it's nice to be able to run RHEL-NIGHT on different generations of servers, and not having a specific version of an operating system for a specific version of a server. So the automotive industry is very much interested in what we're doing, but they're not the only ones looking into us. We have had recently discussions with industries that are less regulated than automotive, but that are still sufficiently critical that they actually rely on software and software stacks that are used in automotive industries, but without necessarily the functional safety certification. One example we've met recently is a mining company that operates, heavy machinery, and they are not as critical from a functional safety perspective. If the engine breaks in the mine, it's probably going to be less dangerous than if your computer crash on the autopilot in the highway. But it is still sufficiently important for them that they're actually looking at these kind of stacks. But down the line, there are also other areas that are heavily regulated, but that will have certifications similar to the one that we are working towards with automotive. You can think like autonomous trains. They'll have a different set of requirements, but there will be a lot of overlaps with what we are looking for in the automotive industries. Medical devices are another area where there are very strong, very complex certification you can achieve, but there is also a lot of overlap with what we do in automotive. So there is industries, if Linux manages to enter in the functional safety areas of automotive, it is the footstep in the door to a number of other areas for highly regulated that may look at what's being done in automotive, that may look at the way the standards is evolving, because there is also work that's being done at Red Hat to make the standards evolve. The standard has been written, I don't know, 20, 30 years ago, something like that, and hasn't really evolved since. And the IT industry has changed tremendously since. The core fundamental of how the standard was written is still applicable today, but the way we do it, and especially the way we do it in open source software, where every single open source software was started by a highly descriptive written requirement document that is highly implemented and covered in 100% test coverage. It's like, I'm sure every open source project in the room is fulfilling all of these requirements. No, really? You do? You have highly described requirement documents, 100% test coverage? But that doesn't mean your project is not actually following the spirit of some of these documents, even if you don't realize them today. So it's one of the things that we're trying to also influence is the ISO community, the standards, to be able to make them amendable to other approach to software development that relies on crowdsourcing reviews, highly available test devices, the test suites. The Linux kernel is probably one of the most scrutinized piece of software. The number of industries, the number of people looking into it, it's a very complex one, but it's also one of the most reviewed piece of software. And yet, it does not today satisfy the ISO standards, but that doesn't mean the spirit, what the ISO standards wants to do, is incompatible with the way the kernel is being developed. So there is work being done there, and that's probably going to open other areas in the future to have these discussions again. Does that answer your question?
Okay, thanks. So any questions from you that we would like to ask?
Apart from functional safety, which we just spoke about, right, and the usual things, the usual security things which we do with well, is there anything else which we need to do with in-vehicle operating system from a security point of view? Like, Dan just said that, if a container is responsible for breaking, it would be valid if there is a denial of service on that container, right? So, I mean, these things we usually don't take care when we look at security from other point of view.
Okay, so I will try to repeat. So the core question was, like, if there are any other areas other than the functional safety which we need to take care about.
My kids used to play a video game called Need for Speed. And so in a vehicle, there are requirements, like you turn the car on within 2 seconds, and these are legal requirements. Within 2 seconds, a bing has to happen, and noise has to be made that tells you to put your seatbelt on. If you put the car into reverse, the reverse camera has to come up within 2 seconds. So there's lots and lots of requirements. So I think there was a talk yesterday on turning on the backup camera within as fast as possible in the Linux kernel. So imagine going from a cold start, the operating system not, and being booted so that it makes a sound within 2 seconds. So there's lots of stuff going on. In the Podman team, we spent probably about 8-10 engineers to try to optimize Podman for starting a container. And when we started out, we were about 2 seconds on a really low-end Raspberry Pi. So we wanted to make the machine as low-end as possible. And we were able to get it up to about 0.3 seconds. So 6 times faster starting. Now, for a human being, if I hit Podman, hit carriage return, the container starts within 1 second. It's not, you don't even notice it. But when you're worried about starting it up, our partner in this is General Motors, and they want us to go negative time. So they want us to create a time machine. Yeah. So. Other things?
The user experience of the the central system in a car is a lot different from what we're used to in a data center. Dan mentioned the boot time requirements. Is you start your car, you don't want to have to wait multiple seconds for the system to be ready. You want to get in your car, start the engine, and drive. Same thing for the application, starting the Podman. When you click the button, you don't want to wait. If you take a Kubernetes cluster, a data center server that will take minutes to start, if Podman takes a few seconds to start the application after that, you don't really care. You've been waiting 5 minutes for the server to reboot anyway. So, a couple of seconds is not hard. The entire user expectations, there are challenges. We are speaking about an edge device that we need to protect physically because the user has access to the device, physical access to the device. So we need to protect it from actually the user tampering with the device, but we also need to protect the software once it's running from, from a non-human triggered random event that will corrupt the software.
Act of God corrupting the file. Basically, if, again, going back to functional safety, you're driving along and all of a sudden you got a corruption on a disk. The system has to realize that, so you can't cause an application to misrun, right? So if a file or an object on the file system gets corrupted, we have to know. So we're looking at like dmverity and different functions. So a big effort has been this thing called ComposeFS, which is a composable file system that we can actually apply some of the rules of dmverity and on FS-verity onto the file system. Basically, so the kernel will, while you're reading a file, the kernel will know that file got corrupted. And so then we can realize it and basically put the car into safety mode, right? Pull the car over to the side of the road into the breakdown lane and call a US thing called AAA and get a tow truck out there to tow the car.
There's also the concept of freedom from interference. So we need to ensure if there's a cascading failure that's happening from the quality management side of things, which is non-safety aspect code, if that's cascading into or affecting or preventing a safety function from delivering its capability, then that would be bad. So we need to ensure that we, for a testing perspective, we have freedom FFI test cases to ensure that there's isolation between the ASIL-B code, safety code, and the non-safety code aspect to ensure there's no interference there.
I have to ask, what will you do if you get kernel panic or segmentation fault or things like that?
So the question.
What happens if we get a segment? No, you answer.
So the question is, what happens if we get a kernel panic or a seg fault? That is one of the core elements of the functional safety aspect. Is we're not supposed to be able to get a seg fault, but that's one of the idea of functional safety. You ensure that the function behaves the way it's supposed to be, and the people using the functions are also due to do functional safety on their application. So it's not only the functional safety basically is a layered approach where we build the operating system, which is built on top of a functionally safety certified firmware, and then functionally safety certified applications will be built on top of a functionally safety certified operating system, which means you can't have a functional safety certified application that does not run on a functionally safety certified operating system. So it's very every layer on the stack, it needs to be certified for the top level application to be.
About, for example, the functional safety of a function that opens a file and writes to it. What happens if you get error?
So one of the things is you have to document all of this. In part of the functional safety is like, okay, the question was what happens if there is an file system disk permission error when you try to write a file. The functional safety documents, all the work that Rachel is doing and documenting in tests comes with basically a pretty big user manual, and we basically get to tell the OEMs, RTFM, and make sure that your code is compliant with the way we describe how it works. So not only are the documentation going to tell you how to use the code, but also what are the different exceptions that will be raised, and how the code, what will be triggered, so that the code can handle such an exception.
Yeah. So I mean, if something goes wrong in the car, So the goal is for the car to know that something went wrong. So it's, again, if you run out of disk space on the car or actually a segmentation fault happens, then we have to relay that information up to the monitoring program that's running on, to see what car, and then the monitoring program will take action. So a classic example would be you're in self-driving mode on the highway, and it'll notify the driver of the car to take over, that the human being has to take over. I'm dropping out of self-driving mode because something went wrong. So from an operating system point of view, our job is to not only describe what happens. If you write code like this, you could have a chance of running out of disk space, right? So that's us describing what functional safety. But if an app on the third node blows up, System D is going to realize it, right? System D knows that this service went down. System D will then tell HERTE, the tool that we have, our Kubernetes, right, our lightweight orchestrator, will then tell HERTE, will then send a message to the main node that's monitoring the system. That HERTE on that system will then relay that to the monitoring app from the vendor, so the car company software, and then the car company software will take action like notifying the human being you have to take over driving, or tell the self-driving car to pull the car over into the breakdown lane, right? So that all has to be realized, right? It's not, just something happened and the car keeps going, right? So.
You have some kind of hardware redundancy in case ground fails?
So before we get to that question, one of the things I wanted to precise that there are basically 4 different levels of functional safety certifications. It's basically called ASIL, and it goes from A to D. And D is the highest level of certifications, and A is the lowest. We are aiming for ASIL B. And it's important to know because things like, as much as we like the brake example, it's actually a bad one because the brakes are not going to be running in an ASIL B environment, they are going to be in an ASIL D environment because these are critical systems. And these kind of certifications it's no longer an operating system, it's a microcontroller. And those microcontrollers are ASIL D and they are very embedded. So even if, if we were to blow, if the node in which we run would blow up, the car would still be, it will remain in a state that it can be driven by someone. All the ASIL D functionally safe certified systems will keep on running. So you'll still be able to steer the car, you'll be able to drive the car, you'll be able to, move to the emergency lane, pull brake, and safety ends. Keep the safety of the integrity of the passenger intact. So we're not looking. We like the brake system because it's something we can easily understand, but it's actually not the best example. But it's easy. It makes it easy to grasp some of the challenges there.
Think more cruise control or lane assist, things like that.
Yeah. And I'm sorry to come back to your question. There was the. Does that answer it? Okay. There was a. I'm sorry.
Which OS will be operating system will be running on those automated cars?
Yeah, I mean the entire operating system is going to be based on top of RHEL, right? We're not building a brand new operating system here. The goal is to take RHEL and prove it's functionally safe. We are going to be modifying slightly the Linux kernel. We're running in real-time kernel, and we're modifying the initRD for quick boot up, things like that. But pretty much, we have to fall back on, Red Hat, 30 years of experience in an operating system and building out RHEL and all the software. Right? We're not building our own glibc. We're not building anything special. For the most part, this is RHEL. So it's Red Hat Enterprise Linux for a car, is what I would say.
Are we looking at other standards for certification? No, we're only looking at ISO 26262. We're also considering ASPICE. which has a lot of overlap with ISO 26262, but just looking at different aspects of that as far as our quality management system, but so far just ISO 26262.
Maybe I will add to this that, like, we have a working group within the ISO who is trying to improve the current version of the standard to be more, like, let's say, aligned with the modern approaches that we are trying to do, right? So it will not be like in the past that when you want to have some kind of functionally safe operating system, you will need to print out like a bunch of books and the wilderness stamps. But it will be much more based on the continuous certification to be able to align with the latest changes, right? So that's one of the part is that we have a people within the ISO standard who is working on improving the ISO standard to be more aligned with the best practices as we have now.
So the question is, if you're targeting SLB, what kind of functional safety software are we speaking about? So infotainment, the question about the infotainment is not functional safety certified. It's called QM, and that's quality managed, and that's basically the rear seat infotainment, the GPS to some extent. So what the stack that we're mostly looking into is the ADAS stack, so the advanced driving assistance systems, basically autopilot. Being able to, sorry? No Netflix, no. Yeah, it's another example that we like to use because it's easy to grasp. But Netflix is not going to be running on top of, Red Hat. It's going to run on Android.
Yeah. So there'll be a separation. ASIL B. We actually support ASIL A, which I'm not even sure what that is, but ASIL A and ASIL B applications. But that could be your entire self-driving capabilities in the vehicle. So there's a lot. Matter of fact, there's very little parts of the system that are ASIL C and ASIL D, just because they're so expensive to. So it's a large framework. QM is quality managed, which basically means it doesn't have to live up to the standards of functional safety, right? If your Netflix app, or what I'm really talking about here is we'll be running Android inside of a VM. If that VM fails, then we just put it aside. Now, what we have to guarantee is that the entire QM system will not interfere with the self-driving car. So the self-driving car gets all the priority over the.
Not necessarily.
No, they want to combine basically 3 or 4 computers total in the car and then have sensors talking to all the rest of the systems.
So right now, the firmware in my car gets updated like once or twice a year. When there's a serious problem, it's a new car. Once there's a serious problem, the cars get traditionally called to the vendor. So what's the future of security and other updates? I mean, the cars are notoriously bad with security.
Yeah. So it's going to be like your cell phone. It's going to get up. That's a. There's lots of questions. We're working back and forth with the vendors on that idea. So they want to have over-the-air updates. So there's certain parts. The operating system itself will be updated maybe twice a year. So the base operating system, but the containers that are running inside of the operating system will be updated on using over-the-air updates. So imagine you, and my thought would be you park the car in the garage and it hooks onto Wi-Fi and downloads it. But the automakers want to be able to update the applications as you're driving around. Now, not replacing the running applications. So imagine you're doing a podman pull as you're driving along the highway. Okay, but not doing a podman restart. okay, to give you, to make it as simple as possible. So they want to have the same experience you have on a cell phone where they can update. But they also want us to, I mean, we just had something come up this week where they talk about how they can protect a USB. They want to update the entire operating system via a USB. So you take it to the dealership, and again, I don't know how this is, if this is US-centric or not, but you have to take the vehicle into the dealership, and the dealership will reflash the operating system from a USB stick. And they want to make sure the USB stick is, you know, certified somehow. And so there's things like that we have to deal with as well. You want to talk about floater at all? It's not floater versus...
No.
Yeah, okay.
You covered that.
So as this is getting built on top of RHEL, do you foresee other features other than performance that other customers might be interested in, like script features that protect dates or something? Not sure if you can speak about that.
So let me know if I got the question correctly. Are there any other features that we are foreseeing in the future about what will run on top of RHEL? Is that correct?
You mentioned getting Podman from scratch to start a container in 2 seconds. For everyone. We may not be that interested because the server takes 5 minutes to boot, but it helps anyway.
Yep.
And there are other features that are being driven by rivals that other customers might.
So are there other features that are driven by the automotive use case that will be used outside of the automotive use case? I think ComposeFS work from Alex is definitely going to be interesting for the entire edge ecosystem, because the entire edge ecosystem is going to have the same, so it doesn't have the safety element, but it still has the security element of the same requirement than the cars. Like it's an edge device that is somewhere far away from a data center, and therefore the user has physical access to it, and we need to protect the system from the user or, you know, its environment. So there are definitely work on ComposeFS that are interesting. Quadlet is something that landed in Podman 4.2, and that was directly driven by the automotive use case. Quadlet is an easy way to manage to start container from systemd services. It's basically if you do to properly start a container using systemd, you have to enter in the exec start line a command that is about 3 or 4 lines long, depending on the width of your terminal. Podman makes this, Quadlet, makes this 2 lines in a text file, and it automatically generates the correct way of invoking Podman runs in your exec start on systemd from a template that's the Quadlet file. And that's something that makes it a lot easier to run containers from systemd. One of the advantages, of course, is one of the other advantages of using that is if in the future we optimize Podman to be, you know, to run in the systemd use case, you know, we do other optimizations for Podman to run container from systemd. You will automatically get these optimizations in Quadlet, and you don't have to remember to go and edit all your service files for a systemd service file to add the new parameters or remove the old ones and so on. So you keep that in Quadlet, and you automatically benefit from it.
Yeah, I'm going to give it to her because there's a lot of functional safety stuff that's funneling back into the RHEL test suites.
Yeah, with functional safety, there's all of the tests that we're taking are derived from the requirements and having to take those and rerun them in vehicle OS. So yeah, there's a lot of rigor depending on how complex the API is, but essentially the APIs are basically based on man page requirements, and then QE has to go and then decompose the man page into low-level requirements of taking something that's ambiguous and breaking it down into functional pieces. So there's a big... What's that?
You get better man pages.
Yeah, and part of that is reviewing the man pages and ensuring that the man pages are doing what the implementation is supposed to be doing. Yeah, but there's a lot of rigor that's going on in the testing aspect with verifying these man pages. So yeah.
Yeah. Also, there's a lot of effort going on right now to get Android to work well inside of. You know, eventually you'll see it'll be easy to run Android inside of Fedora, for instance, as a VM. So there's a lot. Basically, yeah. There's. I mean, Rivos is not a huge organization, but there's about 100 people in Rivos at this point, and everything we're doing is feeding back into other parts of the vehicle. I mean, of the operating system.
Okay, unfortunately we are out of time, so thanks a lot for coming here. Thanks a lot for the great questions. And if you have any additional questions, feel free to come to us and ask, and we will be glad to answer you. Thanks a lot.
So hello and welcome to my talk about stream processing at the edge with Apache Kafka. My name is Jakub Scholz and I work at Red Hat as engineer, and I'm also maintainer of the project called Streamzy, which is Cloud Native Computing Foundation project, which is about running Apache Kafka on Kubernetes. And yeah, obviously that will be one of the things which I will use later in the demo. How many of you know what stream processing is? Right, that's quite a lot of hands. For those who don't know, you can try to imagine it as that the world around us is full of different streams of events and streams of data. For example, in the room like this, when someone opens a door, it's basically an event. Someone opened the door. When someone closed them, someone closed the doors. When someone enters the room or leaves the room, that can be another event. And you can take these events and kind of process them as a stream. So for example, if you take the events that someone entered the room, like now, or left the room, then if you process the whole stream, then you can basically count, okay, one person entered, second person entered, third person entered, then one person left, then 3 person entered. So we have in total 5 people in the room. And that's an information you can build from the stream of events. And then you can use this information for some more things. So I'm quite sure there is some fire code here which says that there is some maximum number of people in this room. So you can, for example, use this information for some alerting, which would say, okay, if there's more than 50 people in this room, then let's send some alert message to some fire marshal, and he will come and say, oh, you two, you are over the number, go out. And then, of course, you can also do things like install some sensors, which would, for example, monitor the temperature, air quality, or the noise level, and then you can kind of combine this information. So how does the noise level depend on the number of people in the room? How does the air quality depend on the number of people in the room? And you can do things such as improve the air conditioning or the audio system depending on the number of the people to, for example, better conserve the energy and so on. So that's kind of how you can imagine stream processing. And now, why does this make sense to do it at the edge? There's a lot of different industries where kind of this pattern fits in. It's connected to how the world is changing, how we are digitalizing everything, and how, for example, we are changing the ways how we produce things such as energy. So you can imagine in agriculture, you can, for example, use some sensors to monitor the fields, whether they have enough water or enough sun, whether there are some animals eating the crops, and so on. In pharmaceutical industry or chemical industry, you can use it to monitor some processes. You can use it to monitor the environment because, for example, a lot of pharmaceuticals or, I don't know, the COVID vaccines, they have very strict limits at which temperature they have to be stored, for example, or that there has to be no sun where they are stored. So all these things can be, again, monitored with stream processing as well, and when you breach some of the rules, it can automatically somewhere mark some batch as damaged, for example. Or you can use it in sports to monitor performance, in manufacturing to monitor, for example, some robots and some car manufacturing line, and when you see that something's going wrong with some robot, you can kind of proactively fix it because stopping the whole line when it breaks will be too expensive. And you can continue like this in transportation, waste management, logistics, telecommunications, energy, retail, and so on. So it kind of fits into all these different areas and all these different industries. And it's good to process the data at the source because that's where they are produced, and it gives you several advantages. So one of them is that you get better latency and speed often. Like the latency, there's one obvious part. If you don't have to send the data, for example, into some cloud and then get them back when they are processed, then you save some network latency, right? But it's also, if you do it somewhere centrally in the cloud, then you might have many locations sending there the data, and you might be queued for processing behind someone else. Whereas if you do it directly at the source, then yeah, you are not queued behind anyone else. You can better control how much processing power you have, and you can make sure that they are processed really quickly and in time. Another advantage is that you are more resilient against things such as outages. Now, in some of the areas, you might be doing the things in the middle of the nowhere, and there might be bad connectivity which is unreliable. But even if you have some retail space, some shop, for example, or supermarket in some shopping mall which has in general good connectivity, it might happen that the connectivity goes down because someone did something wrong, right? And in that case, if you are doing the things locally at the source, at the edge, then you might not need to, for example, close the shop because the connectivity is not working. You can continue to operate as normally. And in some environments, it's kind of not just a question of some problem with the connectivity, but it might be disconnected for a long time by design. If it's a cargo ship somewhere in the middle of the ocean, it might not have the best connectivity possible. Similarly, if it's a plane somewhere over the North Pole, I think there's not good satellite connectivity either. So there are situations kind of where we are by design not connected and where this fits quite well. And last but not least, it obviously impacts also the cost, because if you ever use some public clouds like AWS, you know, for example, that quite often the data transfers are the biggest chunk of your invoice. It's not the VMs or the storage, it's just sending the data here and there. And it's a bit similar here as well. If you don't send the data, if you process them locally, then you can save some costs as well. So I wanted to also touch a bit on what I mean with the edge here, what kind of environment I'm talking here about, because there are many different use cases and they don't always talk about the same thing. So for example, in some use cases, in some situations, people would be talking about edge as some IoT devices, but as I'm talking about using stream processing in Apache Kafka, these would not have really the power to do these things, right? So you might use them in the environment, but that's not what we will be running the stream processing on. Similarly, in some cases, smartphones or tablets might be the thing which might be the edge. And in some use cases, it's completely valid and true, but also quite often, actually, these have enough power to do these things these days. It's not really designed for something like that. So I'm not really talking about those either. But when it comes to things such as single-board computers, such as Raspberry Pi, then that already is something where it can work. Now, Raspberry Pi is not really a professional industry-grade device, but you can use it, you can easily buy it, and yeah, you can do stream processing on it quite easily. And actually, I will use those in the demo at the end. Then in many cases, you might use some consumer PCs or some kind of old PC or some powerful PC lying under the table in some office and kind of running some coffee shop or some supermarket or some fast food chain and so on. And that's, again, that's completely fine, that's completely valid. In some cases, it's really used like that. Yeah, it works. And then, of course, in many cases, it will be just a regular data center with racks and real servers. It's just maybe won't have hundreds of racks or thousands of racks. It will maybe just have just few racks. But yeah, even that's something what can be called edge. And yeah, obviously you can use it in this case as well. So why should you use Apache Kafka for these things, right? That's something I will be focusing on a lot. So why should you even care? And kind of the most lame argument is that it's kind of the leading event streaming platform, right? It's used for these things for years. It's well proven. Is used by many organizations and so on. So yeah, why not use it, right? But there are some more practical arguments as well. And one of them is that it has all the tools you need to do this. So you have the Kafka brokers, which kind of always sit in the middle of the architecture, and they are the thing which kind of receives the messages from some producers and then pass the messages to some consumers, and then you can kind of process them and do whatever you want with them. Then you have the Streams API, which is the actual streams processing engine. Now, the nice thing about it is that it's basically just a library which you can include in your own application. It's not some huge framework with some worker nodes and some schedulers, which is heavy and complicated to run. It's really just something what you take as a library, include in your application, and use its features. And so this kind of being lean kind of fits quite well with the edge as well. But despite that, it actually has quite a lot of features. So you can do all the simple stateless things such as transformations, filtering, enrichments, but you can also do the more sophisticated and heavy things. You can do time windowings, you can do stateful processing with aggregations and storing the data, and all of that can be done while still being scalable, so you can just scale it and run it in multiple instances to get better performance. Then the next part is the Kafka Connect API. So I hope that everyone after the talk will be convinced to use Kafka at the edge, but it would be quite rare that you would use only Kafka there. You would probably have other things as well. So the integration part is important because you want to take the data, be able to send them somewhere else, integrate with other systems, and that's what the Kafka Connect API as a Kafka component does. And then another part is something called Mirror Maker, which can be used to mirror data between different clusters. And that's useful because you can then basically copy these data between the different environments and share them that way as well. And then last but not least, Kafka has also quite a lot of integrations for all kinds of different tools which are not part of the Kafka project itself. So for example, if you would want to do something with AI or machine learning, there's a lot of tools which kind of easily plug into Kafka as well. And you can, for example, pre-train your models somewhere else and then just use them at the edge and plug them into Kafka to kind of read the events and process them. So hopefully that gave you some kind of introduction to the different parts. And now let's have a look at how you can do this as a kind of introduction, as a pattern, which you can use. So typically, you would start with some input data. So you might have some IoT sensors which are feeding you some environment data. You might have some applications running on smartphones or running on some point of sale terminals, which can again feed you the different data. You can have different beacons who monitor how people move through some space. You can have cameras and all other monitoring tools, and all these things can be kind of plugged into it. And then you will have the Kafka brokers, which, as I said, kind of sit in the middle of everywhere, and they store the data and they kind of distribute them. But quite often it would happen that the things such as, for example, IoT devices will not talk directly with Kafka in the Kafka protocol because that's a bit too heavy for that and too complicated. So quite often it will have some kind of bridge sitting in between those. It can be, for example, using MQTT, or it can be using HTTP. And it kind of gets the data in this little bit simpler and easier protocol from the IoT devices, and then it will basically format that as a Kafka connection and pass that to the Kafka brokers. And then from the Kafka brokers, you can kind of connect the different stream processing applications and do the actual stream processing, where you read the data sent by the sensors or by the other input devices, and you will basically do whatever you need to process them. And of course, you can also connect other clients and other applications depending on what exactly you are doing. And that's basically our edge environment. But what's kind of important is that the edge environment doesn't live on its own, right? It wouldn't be edge if it wouldn't be on the edge of something. So there's typically some other part of it as well. I call it here HQ as headquarters, but you can call it central cluster or something like that. And it's again quite typical part of it, where you have something central running, for example, in some cloud or really in some headquarters, in some on-prem data center, and you want to link these two parts. So that's where kind of the Mirror Maker tool fits in, because it can basically mirror the data between the different Kafka clusters. And that's quite important, because when you do the processing, maybe you aggregate something and then want to push the data into the central information system of the company or of the organization, but also it can work in the other way around. So quite often you, for example, have some reference data or some master data which you are managing in the central cloud, in the central environment through some other tools. And then you always need to kind of take them and synchronize them to the edge locations so that they can use the latest reference data. So that's what you can do with Mirror Maker. And then what's also important is that usually you don't have just a single edge and the central cloud. Usually you have many of these edge locations, right? So you need to be able to manage them and monitor them in some efficient way, because you don't really want to SSH into all of these and then install something or upgrade something or check if it's still running. So you want something that gives you as little work as possible. And that's where the things such as Kubernetes or the Kafka operators as Strimzi, which will help you run all these components, come in, because they will do a lot of these things for you and make it much easier for you to manage this whole architecture. One of the advantages is that it allows you to run the same software everywhere. So you can use Kubernetes and you can use Strimzi or the other operators if you would use database, for example. You can use them in the central cloud, but you can use them in the edge locations. And even at the edge locations, for example, you can use them on different hardware platforms. You can have different situations. Everywhere you can use the same tools. You don't need to learn new things every single time, and you can use them exactly in the same way. So you know that when you are fixing something on one environment, then it will be exactly the same environment as the others. But thanks to the Kubernetes and operators, you should not actually need this that much, because they kind of help you with making the environment resilient and self-sustaining, right? So the Kubernetes, they will take care of restarting the processes. The operators will basically make sure that the applications are running, that they are upgraded properly, that they are maintained, that they are monitored, that their certificates are renewed, and all these things for you. And they kind of do this whole job for you, and you don't need to take care of it that much. And then finally, there's a lot of tooling around automation, which is available for Kubernetes, such as the different GitOps tools, Argo, Flux, and so on. And you can use those to kind of manage these configurations. So with operators, you have it all in declarative manner, where you have some YAMLs, you can kind of store them in your Git environment. And then you can use these tools to kind of roll it out to all the different locations in various patterns. So that makes your life much easier as well. So let's have a look at a demo. At the end, I have there a link which gives you the GitHub repo with all the source codes and so on, so that you can look into that in a bit more detail. But basically, what I have, it's running at home in my home lab, and there's some ESP32-based sensor board with some sensors for temperature and humidity and air pressure and so on. And that's then connected over Wi-Fi to the Kubernetes cluster, which is running there. And it's actually using an HTTP bridge to kind of communicate with the Kafka cluster. So the board sends HTTP request, and the bridge converts it to the Kafka broker. And then it does the stream processing using the Kafka Streams API application, which basically, just to demonstrate something simple, it does kind of 1-minute windows, and over the windows it calculates the average values and then sends them into another Kafka topic. And these are then mirrored by the Mirror Maker into the kind of central cloud, where there is a simple application which basically takes these data and visualizes them centrally. So it's not really industry-grade equipment, but it's really running on real hardware. It's not just some software emulated thing. So it's using this ESP32 board with the sensors, and it's using it in MicroPython. And then I actually have a Raspberry Pi cluster, which actually has 3 nodes, not 4 nodes when I did the demo. And that's running the K3S Kubernetes distribution across it, and it's using the Strimzi operator to run the Apache Kafka components for us. So I hope you will forgive me for using recording, but actually running in resilient and self-sustaining matter at my home behind the NUT, so it's not that easy to do this live. But let's first have a look at how the IoT board looks like. So as I said, it's using MicroPython. That's kind of a cut-down version of Python. If you don't like Python, don't worry. I'm not biggest fan either, but it's actually quite easy to use, and even with a little knowledge, you can easily write some things. And what you see here are the basic files for it. The BME280 is the library for working with the sensors. And then the boot.py script, that's kind of what's called when the board starts. And that's just some initialization work, like connecting to the Wi-Fi so that it can send the data and things like that. And then in the second file, in the main.py file, that's what's actually running there all the time and doing the actual work. And it basically first loads the library for working with the sensor. Then it initializes some LED lights to kind of use to signal some problems. So it will be kind of switched on if something stops working. And then it kind of configures the different data, like the location of the sensor and the URL of the HTTP bridge, where it kind of sends the request. And then it's basically running in a while loop every second, and it reads the data from the sensors. It formats a JSON message from it, which it then sends using HTTP post to the Kafka broker as a message. And when that succeeds, then great, let's do another loop. And when it fails, then it kind of just switches on the LED light to kind of indicate that yeah, something's wrong. So that's basically how the IoT board looks like. And now let's have a look at the edge location. As I said, it's kind of Kubernetes cluster. It actually has 3 nodes when I recorded the demo because I had one of them switched off. But it's running the K3S distribution, and when I check the pods which are running there, you can see the Strimzi operator, which is kind of running all the Kafka components. And then you can see the Kafka cluster with Kafka pod and Zookeeper pod. And you can see also the entity operator, which is used to manage users for security and topics for where data are sent. And then we have the mirror maker, which is doing the mirroring. And then finally we have the bridge, which is doing the bridging between the HTTP world where the IoT device sends the data and the Kafka broker. And now what we can do, because it's running, we can start a Kafka consumer and connect it to the topic in the Kafka broker where the data are being sent from the device. It's actually using this Wi-Fi AP pod, which is actually running in a pod, the whole Wi-Fi setup. I find that quite neat, but I don't take any credit for it. I think I copied it from some colleagues who maybe copied it somewhere else. But yeah, now let's run the consumer, and that should show the kind of raw data as they are being sent by the sensor. So we should see roughly every second a message in the JSON format with the readings from the sensor. So it takes a few seconds to start the consumer pod. And now you can see the messages as they are kind of coming in through the bridge from the IoT device. And once we have them in the Kafka broker, we can move on to the stream processing. So there's one other pod running in this namespace, and that's the aggregator pod, which is running the Kafka Streams API application, which is actually running inside this Quarkus framework or toolkit, which kind of makes it easier to just run it, and it does some special tricks in the build time to kind of optimize it. But what it's basically doing is it's reading the data from the Kafka broker every second, and it's creating 1-minute windows, window after window over them, and then calculating the average for given minute. And then when the minute window ends, it will basically take the average value and send it to another topic in the Kafka cluster. Now, obviously, this is more for demonstration purposes. It's not the most sophisticated processing possible, but it should kind of give you idea about how this can work. And now when I open a consumer against this topic with aggregated data, we should see again basically the same message, but now it should be sent just every minute because it's basically a result of the aggregation, and that's kind of the average value which kind of softens out the numbers we are getting from the sensor. So that's kind of the edge location. And then the last part is the central location, where we kind of get the data from the edge locations. Like I have at home right now only one, but in reality you would have many of them feeding the data there. And what we can see here is again the familiar thing, the Streamzy operator on the Kubernetes cluster running the whole Kafka cluster. This time it's a bit bigger, so that it can handle more data and more things. It has also some more components. But then there is this front-end application which basically reads the mirror data from the edge, and then it shows them on a map, or it also kind of keeps them for the history and shows them in Prometheus, so that you can kind of look how the values were evolving. Yeah, what we can check also is how the data are being mirrored from the edge location. So I will again run the consumer. It's the same as the last time, but this time it connects to the central cluster and not to the Kafka cluster at the edge. And we should again see basically the same messages, but this time these are the mirrored messages mirrored using the mirror maker. And yeah, so here's one. And if we will wait another minute, we will get next one and so on. But let's switch to the browser and just ignore this for development purposes. That's when you use Google Maps without entering the production API key. But what you can see is it just shows the map, and it shows the pin with the location of the sensor, and then it gives you the details. And when you click on it, you can kind of get to the Prometheus chart, which gives you the history and shows you how it was evolving. So that's kind of the demo part. It's done simple so that it doesn't have too many things which are kind of not focusing on the pattern, but should demonstrate well how Kafka helps in this area, hopefully. And that's it for the talk. This is the URL where you can find the demo. It will redirect you to the GitHub repository. And yeah, thanks for listening. Thanks for watching. And if you have any questions, we should have some time for that. Yeah.
Quick one. If I run Kafka native with the standard port 1992 or the native Kafka application, I move it to a Kubernetes environment. I cannot export the port. How do I get the applications that talk to the native API talking to the containerized Kubernetes version?
So it's quite complicated because you would need to create different listeners in, just to repeat the question was if someone runs the Kafka in the containerized Kubernetes environment, how to get access to it kind of from the outside. And it's not easy because of how kind of Kafka has its own discovery mechanism, which makes this quite complicated. But basically you would need to configure the listeners in the way that you have, for example, multiple listeners. One of them will be kind of for the internal applications running inside the Kubernetes cluster, and other one will be for the applications running outside. And you have to use in the other one, for example, addresses of some node port or some load balancer address in there to kind of advertise it to the clients, and then use this listener for it. So if you would use the Streamzy to run it on Kubernetes, then kind of it has 4 different types of listeners, like using load balancer, using ingress, using OpenShift route, and you can kind of just configure them, and it kind of does all these things in the background for you, and then just gives you the address where to configure the client on. But yeah, you would basically need to play with the advertised host configuration in the Kafka config if you would kind of do it yourself. Any other questions? Yeah. So the question is, if you would have multiple edge locations with basically multiple mirror makers synchronizing their own data, if it would be synchronized into the same topic or into a different topic for each location. Just to repeat the question. And I think it depends a bit, like with a project like this where we are just sending some sensor data, the same topic makes most sense because then it's much easier to consume it. But there definitely might be some cases where different topics might make more sense, where, for example, I don't know, you work for some organization with just some other kind of divisions and so on. Yep.
HTTP bridge, is this a standard component you can download somewhere, or is it, can you use several projects for that?
So the question is about HTTP bridge, if it's a standard component or if that's different projects and so on. It's actually what I'm using here is directly from the Streamzy project, which has its own HTTP bridge. And you can basically deploy it with the operator just by specifying a custom resource. So that's kind of easiest, and that's what I use there. There are some other bridge components out there as well. There's the Confluent REST proxy, which does HTTP proxying as well. Confluent has an MQTT bridge as well, which you can use if you want MQTT, for example. And there are others as well. So you can kind of use what I used as a Streamzy maintainer was obviously the Streamzy bridge. But you can, if you would want, you can use others as well. But yeah, I use, yeah. Yep.
How do you configure your aggregation paths?
Sorry, what?
The aggregation, Streams API. It obviously listens for,
Yeah, so the question was how do I configure the aggregation part? So it's using the Kafka Streams API. I should have prepared it so I should have showed the source code, but the source codes for it are actually in the GitHub repository as well. But it basically, in the Streams API, you just say start from this topic and specify the CERDES for kind of decoding, deserializing, and serializing the messages into Java, basically. And then you just get the messages as object, and you can work with them in the Streams API DSL. So you just start with this from, and that basically, in this case, that gives you kind of the data, and then you just use the DSL to say, okay, with windowing, with 1 minute windows, and then the most complicated part of it is actually writing the custom aggregation to kind of do the averages, but otherwise it's quite simple. If you check the GitHub repo, there's it's like 3 Java files all together or something like that. Yep. So I'm not sure exactly how easy. I don't think it would be that easy to use it to distribute commands, which would be to specific edge locations, right? Because you would, for example, need to have different topics for kind of each location to be able to say, okay, location with this ID, do this. Or you would need to mirror the commands for everyone to every edge location and then let the edge location, for example, filter it out, whether it's for it. But it's like super useful if you have some reference data, like if you, I don't know, use it in some supermarket to update all these digital price tags. Then if someone changes it in the central, change the prices, you can kind of roll out the update to all the edge locations this way, for example, or other kind of reference data where basically the same data can be sent everywhere and applied to all locations. I think that's where it fits a bit better than some kind of command pattern. Anything else? In that case, thanks for joining me and thanks for your time.
first day was actually quite busy. Well, the Ansible guys, it was full.
Oh yeah, it's the famous. Rapid.
Super high. Yeah, good to go?
Well, good afternoon, everyone. After lunch, it's always going to be an interesting session, but at least we're not talking about security, so it should be fun. My name is Faz. I'm one of the EMEA specialist solution architects at Red Hat, and I focus on Kubernetes cluster management and automation.
I'm Luca Ferrari, I'm Italian, and I'm an edge computing specialist, so you might have heard Red Hat recently is investing in edge quite a bit, and I have a background in integration and API management.
So a few years ago, I had a call from my father's neighbor. They called to tell me that they heard my dad's little dog barking in the garden. And when they went to find out what the problem was, they found my father lying down on the patio, unable to get up. So he had a fall and he couldn't manage to get himself back up. Fortunately, that day, they called the ambulance, and by the time I made it there, my dad got the medical attention he needed. But this wasn't the only time this was happening. My dad suffered from Parkinson's and Parkinson's-related dementia. So if he didn't have someone with him all the time to remind him of his limitations, he would set off on walks, and sadly sometimes on that cold day, the floor would be slippery, he would have a fall, and he couldn't get himself back up. Sadly, as probably a lot of you are aware, his story is not unique. In fact, according to the National Safety Council in US, a big chunk of falls that happen at home and cause preventable injuries and sadly injury-related deaths are related to falls. And these falls are very common amongst the elderly. And you know, we're facing an aging population, so this problem is only going to get worse and worse. So if the elderly don't get the care they need at home, they're very likely to have a fall. They might neglect themselves and they end up in A&E in the hospital. And that means pressure on the health and social care. So we're just looking into see how we can use technology to help with this problem. The reason that we are looking into this assistive care today is because the hospitals are already overwhelmed with a lot of day-to-day problems. They have a lot of legacy systems and devices that they need to integrate and maintain. They produce a large amount of unstructured data by the medical equipment that needs to be maintained, and they need to be compliant with industry standards. Patients are expecting to be able to look at the data online. And on top of this, the hospitals don't have a big IT budget or IT teams to be able to resolve these problems. And that's why we're trying to see how we can use open source to relieve this burden of at least with the elderly and assisted living from the hospitals.
Yeah, so given the challenges we've seen, there are several advantages of using an edge computing approach when it comes to assistive care and using open source at all layers. So first of all, in terms of Red Hat project and products, you can see that we started adopting at the edge the same platform that we adopt at the core, which is basically Kubernetes. So that brings manageability advantages. So the team doesn't have to learn a new tool, basically, or new technology. Then there is security by default at all levels. So through tools like ACS, Advanced Cluster Security, you can implement a policy that automatically secure new clusters, or in the case of assisted care, secure new homes. Then there is a whole partner ecosystem. So I mean, I don't have to explain it to you, but the power of community here is pretty strong. So we can, for example, connect to legacy protocols through library developed by community. And we have a whole set of partner products that can be deployed at the edge or at the core indifferently. And then eventually manageability and scale. So when you think about an edge architecture, what comes to mind is actually day 2 or thinking about deploying the second, third, or eventually 100 cluster after the first one. So deploying the first one and managing the first one is quite easy, but what about managing at scale? So then you have tools like Advanced Cluster Manager that help you with that scenario. So we came up with actually a reference architecture in this case, and with the specific use case of assistive care. And we look into literature on what are the type of sensors and scenario that can help detect a possible death at home, let's just say. So there's a full mix of technology, as you can see here, quite a recipe. I'm pretty sure you're familiar if you're been working a little bit with home automation with Raspberry and Arduino, so I will not explain a lot about those. We use two different messaging technologies, so you might have heard of NQ Broker as in Artemis as a project. So that's a store and forward broker. We used it for MQTT messages, but it's a multi-protocol broker. Then we use NQ Streams, so that's actually Red Hat packaging of Kafka. So you might know the project as Streamzy. And we use it for event streaming scenarios, right? So when you want to process data at the core. I don't think I need to explain anything about OpenShift. Faz will be able to answer any question on ACM after the session. And we use Camel with Quarkus, so there are also quite a number of talks today about Quarkus. There are now extensions to actually run Camel integration on top of Quarkus runtime, so to make integration even lighter. This is for all the scenario where you want to integrate legacy or industrial protocols, for example, at the edge. Then we use for the monitoring and presentation part Grafana and Timescale. Timescale is actually a time series database that's included as part of Drogue that you see here. And Grafana, well, allows you to build custom dashboards. So in case the hospital wants to have current state monitoring of what's the patient scenario, they can do that. Then we use Ansible for all the event-driven automation case that Faz is going to explain in a bit. And I'll deep dive a little bit more into Edge Impulse and Drogue. So Edge Impulse is, well, it's a, let's just call it a studio, an online studio for MLOps. So if you're familiar with OpenShift data science, it's not that dissimilar. The difference is that it's highly focused on machine learning at the edge on very low resource devices. So that's especially important because a lot of this sensor and this platform are not really single node OpenShift or are not really beefy, right? So if you want to run some machine learning model on stuff like Raspberry, that's really good, good tool. The other interesting element that you can see here is that you can start building your model directly on your smartphone and then deploy it as a test case on your smartphone, either Android or Apple. This is Drogue. Instead, this is a Red Hat project. You might want to take a look at it if you're interested into processing data and coming from IoT environment. And there is a whole set of layers. So in this case, this was the diagram was more focused on automotive use case. So you can see the little car there. But basically, there are two main concepts, the devices and the application. So the devices are at the left-hand side. They are basically all your sensors and actuators. And then you have the application. So the application are what the end user might use or develop. And typically, several devices are associated to one or more applications. So you have an ingestion point through the endpoints to the left. So Drogue supports HTTP, HOOP, and MQTT. Then eventually there's a data streaming component through enqueue streams, so you see there Kafka. There is a whole set of authentication, both related to devices and applications with Keycloak. And you also have a set of device management and device registering functionalities. Okay. Eventually, the data that can be processed, filtered, and even there's a basic rule engine is exposed through integration through the right-hand side, where you can see WebSockets, MQTT, Kafka, and even serverless events. So this is the architecture we came up with. As I was explaining before, we used enqueue broker to ingest the events coming through MQTT communication from the sensors. Then let me just maybe switch to the actual data flow. So then this is, yeah, it is animating. So then the messages are eventually stored in the event streaming part of Drogue. Drogue will apply some filtering, so for example, will not actually activate any alert in specific scenarios. It will also store for historic purpose all the events in the timescale DB for later exploration. And then it will send, and then Ansible will actually get triggered on specific situation through events on a specific topic on enqueue streams. Eventually, Ansible will trigger a call, or in our case, a message to Telegram. So the idea here is that given specific scenarios that we'll explain soon, a nurse will be alerted that there is a patient to be visited. She will travel to the assisted house.
Right, so the use cases we've tried to implement using the technology you just saw are, one of them is the fall detection alarm as a wearable, and the other one is a fridge usage monitor, so essentially just to monitor the state of whether the fridge door is open and closed, and then decide later on based on that information what we need to do. And also the scenario of combining these two through sensor fusion. Who knows about sensor fusion? Who has worked with the concept of sensor fusion before? Okay, so sensor fusion is just the process of combining the data that we get from different sensors or different disparate sources of information in order to get a better understanding or a clear picture of the whole situation. On a high level, that's the explanation. So it's just combining the data that we get from our sensors. So for the fridge usage monitor, so we divided the use cases into two parts. I worked on the fridge usage monitor, and Luca worked on the fall detection alarm. For the fridge usage monitor, what I used was an Arduino Uno Wi-Fi and the reed switch connected to it. The reed switch is just an electromagnetic switch that, based on the voltage high or low, you can decide whether the door is based on the magnet being close to each other. You get a high or low voltage, and then you can detect whether the door is open or closed. So I started implementing the code on Arduino Wi-Fi, which is this little board here, which worked really well to begin with and gave me a false sense of security. But as I went along and I was trying to implement SSL, it took me a long time to get to do that. And then I realized the libraries that I was using on this Arduino Wi-Fi do not support SSL properly. So then I switched over to this ESP WeMask board, and I managed to get SSL working on that, which was a good success. And just to show you a little bit of the code snippet from the Arduino, as you can see, we're just reading the serial, the data that comes through the serial board, and we're just sending the information through using the MQTT client that's available on Arduino libraries. We're sending the information to our MQTT broker. In case anyone hasn't come across MQTT broker, it's just a lightweight network protocol for PubSub and messaging. And
the other use case was based on an interesting scenario and device. So the device you see on the left-hand side is this small thing. So interestingly enough, this can run a very basic TensorFlow-Lite model, and you can deploy it using Edge Impulse, as I was saying before. And then I basically aggregate all the measurements through Bluetooth on a Raspberry Pi. So this then communicates back to the NQ broker in Snow. So I'm not going to show you any C++ code because I'm not really proficient in C++, but basically Edge Impulse generates, after you, I'm going to explain it afterwards, but the way it works, you generate and train the model, and then you can export it in several ways. One of them is just an agnostic model, which is just in C++, means you can deploy it almost anywhere. And as you can see, there's the structure, the model parameters, the SDK, which means which is the runtime, and then the actual TensorFlow-Lite model. So the way it works, as I was saying before, if you've been experimenting with OpenShift Data Science or Open Data Hub, I think it's the upstream. It's just a standard MLOps platform, so you get to design the model using several libraries, you get to train it and collect new data sets, you get to test the accuracy of the model and eventually deploy it on several edge targets. So this is an example of the interface. As you can see here, in our case, we were interested into measuring the acceleration in XYZ axis. So that's one thing the Nano can do. There are other sensor packages on the Nano. And based on this variation, the model basically identifies whether this is somebody falling or not. Eventually, you get to be able to deploy on several tiny platforms. So as you can see, there are several Arduino platforms supported, but there are other certified platforms for Edge Impulse. So there is an alternative to this tool, which is not online, it's completely on-premise, which is TinyML. So if you want to explore that instead of using the cloud approach, it's also worth it. This was basically to recap a little bit. So we were up to the sensor layer, and eventually we decided to introduce NQ Broker to actually store the messages for persistence. So somebody might ask why the sensors are not directly communicating with the cloud. The OpenShift platform is for persistence and resiliency reasons. So we configure NQ Broker so that it exposed among the several protocols it support MQTT. And as you can see, we created a queue and an address related to this type of traffic, so the Arduino one. And you can see an example of messages. So you can browse the queue and see the content of the message. And then I configure also Drogue, so I created an application corresponding to the end user application. So in this case, it was just a notifier application. And this notifier application had associated several sensors. So as you can see, I can also create an IoT gateway in Drogue, and you can create a hierarchy between the actual IoT gateway and the other sensors.
Okay, so far we've seen how we're just getting the data from our sensor. They come to AMQ Broker, redirected to Drogue, and as a part of Drogue, as you can see, there's an AMQ Streams section that comes with Drogue. So now the notification part involves the data from AMQ Streams or Kafka and Ansible EDA or event-driven automation. So what you see here is an example of the event-driven automation using Ansible. This is the main component is called the rulebook. Within the rulebook, we've got two sections, which we've got the sources section, which we have different plugin sources for it. In this case, we're using Kafka, and then we've got the rules section, which based on a condition, an action is triggered. And as you can see, it's quite simple, the usual Ansible style. So we're just saying that if you're getting that condition that the door closing is detected from Kafka, trigger a playbook. And the playbook we've got, And that's just the automation controller. As you can see, that playbook is just running in there. So just open the automation controller, write that playbook. And the playbook is pretty simple. We're just using the collection, Telegram collections, to send the notification. And eventually, when that is done, we will get the notification message, or the carer or the family member or the nurse will get the notification on their phone, whether a fall is detected or what's happening with the fridge door, and so forth. So this is what we've done so far with these 2 use cases. Still work in progress. We're still working on improving them, and we're hoping to start introducing more use cases to this POC. So you may have noticed we haven't talked about Camel Caucus part of the architecture because we haven't implemented it yet, but we will. We're looking into implementing some sort of local level 1 alerting using Camel. And we haven't talked about Rackham because we've been focusing on the application side of this POC and what actually we can do with it. Rackham takes care of the infrastructure side. We have used ACM in order to provision our single node OpenShift cluster and also implement the configuration and application on it. And that's just, as I'm sure most of you are familiar with this if you work with Rackham, that's just the clusters as you can see in there.
So to conclude on some lesson learned, so you might have already been fighting with certificates. So TLS certificate and DNS are usually the culprits of issues when it comes to development and integration. Also the test case I was showing with the Nano, it's all through a USB cable. Even if you have a really long one, you might actually think about adding batteries so that somebody can wear it on the wrist. Also, it was quite hard personally to develop this joint project since we're not in the same country, so we are also not really developers, so we had a tough time using remote calls for pair programming, let's just say. Also, we were showing the single node OpenShift on AWS. My initial idea was to bring an industrial grade server to the stage, but it's really hard to actually connect to both power and network in general. We also were trying to have fast connecting to my home lab for some tests, but VPN access through internet is not as easy as it looks like. And eventually, I don't know if you guys have been experimenting with bot security with the recent version of OpenShift, but it can be quite tough if you try to run something. So just to remind you what you can explore in terms of initiatives inside Red Hat. So there's a healthcare validated pattern. So I don't know if you heard about validated pattern. This is dedicated to basically analyzing medical images and providing a better diagnosis to doctors. This is all done through OpenShift Data Science that I mentioned before. And basically what validated pattern is really just a way to, just a POC code that you can re-execute. It's stored in GitHub, so you can contribute, and it's designed by industry and by use case, basically.
So yeah, just as a recap of the whole thing, we're just putting this effort into using open source for assisted care. So hopefully when it gets our time to retire, we will have a happy and healthy retirement.
Any question on anything? Yeah, sure.
Yeah, if you go back to the architecture picture.
Yeah. Yeah.
Yeah, maybe I missed it. The single node OpenShift runs at the patient's home as an edge
Yes.
device? Okay.
Yeah, the idea is to run it there. As you probably, there were a couple sessions. You can even run microshift if you have limited hardware resources. It's given the workload we are working with, it will run on microshift as well.
Yeah.
I'm wondering what is fall on the ground. So how do you measure if it works correctly?
So actually there is... So if I understood correctly, the question is where do you get the data for the model to be precise, right? The falling model to be... So actually there is quite a data set already available. I didn't have to train it myself, but with Edge Impulse you can even train it yourself and add your own data to the model quite easily.
I see, thank you.
Yeah.
Why are they using Ansible in this integration?
We just wanted to just incorporate as many Red Hat products as we could, given the title of the talk is just using Red Hat technologies. So that was one of the main reasons behind using EDA.
Yeah, but I guess also the advantage is that you can automate other stuff, so you can leverage it for future use cases as well. So.
You can integrate also joke with other events in order to make more complex scenarios, like for example, feed other instead of using ADA directly using Cloud EDA, you can use joke in order to connect with other components and make much complex, for example, scenarios and do business analytics for adding, I don't know, an app to the nurses or to the end users as well to check, for example, if your parent is okay and try to meet.
Yeah, so actually the output is cloud events, which is a standard, so you can trigger even stuff on AWS, I guess, or other platforms. Yeah. Cool. Thank you.
Thank you.
So, good afternoon. My name is Josef Blich, and I work in Brno, and I live in Kuřim. And I'm one of 2.5 developers of Nemo Mobile. This talk topic is the question. The question is if the Nemo Mobile is suitable for automotive. So, first of all, who are here some automotive professionals? Okay, so I apologize. you will see why. It's not really professional or for professional use, probably, or maybe we will see. Let's try to answer the question. To answer that question, we have to look what is actually Nemo Mobile. I will go through current status of the project. I will tell a little bit about its architecture. And I have some automotive demo also. And yeah, I have a few details about the project. You can hear mobile in the name of the project. And it can tell you that we are focusing on the mobile phones. So we would like to have mobile phone with own Linux distribution to make phone calls, etc. Currently, we are developing that on PinePhone. I have one device here, so please try it, play with that. There are no sensitive data, so you can do whatever you want. If it crashes, then it crashes. If you don't return it to me, you have to develop it instead of me. So be careful. You can try to run it also on PinePhone Pro. I have proof of concept on QT tablet. Well, I have image, it was running, but right now I don't have device. I'm using it in my KVM virtual machine. You can find in ARM profiles repository list of devices and which are supported, so you can try other device. Some people was trying to run this distribution on Android devices, or they are using Halium layer, which allows to run distribution with an Android device. So it was, yeah, on the picture you can see the Volaphone. So that's the code name is Yggdrasil. I seen some Xiaomi, Redmi devices and others. If you are interested, you may try your own device, but it's more work to do. So the operating system looks like this. It's basically open source rework of Sailfish OS UI. So we have 3 screens, one with notification, one with task list, and one is app launcher. So we have some UI. We are using Mallet keyboard to be able to write something. It's great that you can connect to Wi-Fi and debug it, not only with serial cable, but also with Wi-Fi or through Wi-Fi. USB networking also works quite good. We can control the phone using buttons, so you can turn it off, you can change volume. Of course, as geeks, we need terminal. And via terminal, you can install applications using Pacman. You can see Pacman, it means we are using distribution based on Arch Linux, namely Manjaro. Manjaro provides to us many packages as kernel, AutoTools, CMake, GCC, and others. With Nemo Mobile, we are extending that with roughly 150 packages. Roughly 70% are taken from MER project. If you don't know MER project, it's Me Go Resurrected. It is part of stack which is used in Sailfish OS, and Yola is maintaining big part of those libraries, which is great. Yeah, you can see some examples of those libraries. We have own fork of Ono. So as you can see, we are not using Network Manager and Modem Manager. We are using Conman instead of Network Manager. We are using Ophono instead of Modem Manager. Yes, again, some examples of applications. So this is settings, application, and browser. If you know Sailfish OS, then you know that Sailfish OS is using Qt5.6, which is, I would say, ancient. One of reasons to move to Manjaro was to use up-to-date Qt. So currently we are using Qt5.15. We have own Qt Quick Controls. Those Qt Quick Controls are based on Qt Quick Controls 1, which are incompatible with Qt6. We are working on port for Qt6 right now. It is a lot of work, and we are moving slowly because it's like weekend project. It's not our day job, so it's really slow. We are pushing back patches to Sailfish OS, to Yola, and they are merging it mostly. We are using some middleware or like wrappers around other libraries, which are named Nemo QML plugin, which is basically interface into QML to use other things like time daemon, which can provide wake-ups and so on. We have own UI application, we call that Glacier, and yeah, those are examples of user experience you can have. Like 80% of screens you can see on the device. Okay, that was Nemo itself. And now let's try to answer the questions. It is ready for automotive? No, that's short answer. I was on FOSDEM this year, and there were some stand with automotive demo, and they told me, if you expect that you will get that device and put it into car, you shouldn't do that. You shouldn't expect that. It's platform. It's 80% ready. So I told to myself, okay, now we are speaking about percentage of matching of some expectations. So let's try to do that with Nemo. So I think we have at least few percent of match with automotive expectations. So I have found some paper from Clomark, Anders, and Wikingson, and they have this picture of architecture. And if you look carefully, I know the letters are small, you can see, okay, home screen. We have home screen, so 1 point for us. Bluetooth, Wi-Fi. Okay, we can connect to Bluetooth, we can connect to Wi-Fi. Wow, we have so much. AM, FM tuner, okay, we don't have that. Actually, behind the whole stack in Nemo for telephony, it's actually necessary to work with audio profiles, because when you want to make phone call on mobile phone, you need to switch profile. When you receiving phone call, you have to switch the profile back after the phone call is over. You need to support Bluetooth headsets and so on. So we have quite a lot of packages which are managing those audio profiles. So I expect we can be close to that requirement. We have some media browser, telephony, contacts, navigation, sort of. I don't know why social media apps are mentioned twice. Maybe more social media is better. But we don't have them. And the email application doesn't work quite well right now, so I would say we don't have it so far. Yeah, we can go deeper in the stack. So we have some native HMI. We have some other things like location services. We have some kernel for sure. So we have many components in demo, and it is hard to say if it's like 50% of match or how much. It's up to you actually. That you should provide answer to me if you think if it fits. For sure, Nemo Mobile needs a lot of love. There are a lot of bugs, but it can be platform for also for automotive. And now the question is to you. What are your expectations? Do you have some? Like fast boot of device, boot up in 2 seconds or something? No? No one. Okay. Let's move forward. I made some demonstration application with that OBD2 Bluetooth thing for $10 or something, and yeah, I was trying to make it work, and I did actually fail, and I don't know why. So maybe some expert can help me. I connected to device, paired it, made it trusted, connected to that. Using RFCOM command, I have created block device in dev and sent ATZ command using Minicom, and nothing happened. When I tried on other device, like on X86, it was working, but not on the phone, not on ARM, and I don't know why. So maybe someone can help me. I was not so successful in that way. For the demonstration, I was trying to make GPS working, and it is also not so easy. There are many combinations how you can connect it together. Modern distributions are using GeoClue interface in version 2, and it has some provider in Qt, maybe most probably also in GTK. And if you call some it's Qt location. If you call some positioning source, start updates, you can get data from GPS. For some reasons, we realized that GeoClue 2 doesn't work for us as we need it. We had some issues probably with Mozilla Location Service, the GeoClue provider, and therefore we switched to GeoClue 1, which is not good thing. I think we need to change it back to GeoClue 2, but it needs some time and some love. And as a consequence, we are taking Qt from Manjaro. So it has all shared objects for all providers, so GeoClue 1 and GeoClue 2, but it prefers GeoClue for some reasons. So if you want to do it on the device right now, you need to remove user libqt providers geoclue2.so file. Then you restart device probably, or application which is using provider, and then you can get to GeoClue1. And from GeoClue1 you need to get to GPSD or Mozilla Location Services, so MLS DB provider inside. Then you will have the position. If you want to go from the other side, because the provider goes then to GPSD, then you can start GPSD and debug it using CGPS, and you will get data. As far as I know, the GeoClue2 access directly to GPS, and it is a little bit easier, and Mozilla Location Service should work somehow, but I haven't digged into it deeply so far. Okay, that was about my proof of concept application. If you want to start develop Nemo Mobile, we have pretty nice website which contains description how you can install that on PinePhone. It's basically you will take the SD card and you will copy image on the SD card, then you put it into PinePhone and it boots. So it's pretty easy. We have description how to install SDK. Well, it means that you will install those packages to Manjaro virtual machine, and then you can compile everything. Yeah, we have some description of our Qt quick controls, because yeah, they have specific API, and yeah, most important is that you need to know the names of components to be able to choose the right one. Yeah, please try to contribute with code. That is like the best option for me. I was writing some blog posts about progress of distribution. So every month, one blog post with news about project. I was adding always section bug to start with, but there are so many bugs that we need to solve them first. So you may look into those blog posts and you will find what is not working as we need. As I said, we are using Manjaro, so it is using package build scripts to rebuild instead of spec files, but it is like very easy to understand if you can work with RPM. It is simply bash script which contains functions, and each function corresponds to section is in RPM spec file. It has some limitations, but it is much simpler than RPM, I would say. If you want to start, you will probably need to go to Nemo packaging repository. It contains package builds for all our 150 packages. So you can start, if you want to debug calendar, then you will start with Glacier calendar repository. You will see how it is built, and you can what dependencies it have, and you can like track it down to issue. Then when you have a package, you can build it locally using make package, or build ARM package like for cross compilation, and then you will probably build some image. So build ARM image will take the repository you will provide and will produce the image you can install on your device. There is a Git repository which is called ARM profiles, and it contains list of devices which are supported by Manjaro. We are happy if you contribute also with something else than code. You can translate it, you can make some documentation. We are looking for some user interface drafts to implement. So if you are a graphical designer, you can draw something for us, and we will be happy that we can try to implement that. Yeah, and if you spread the information, and if you find some other developer who can help with project, if you write a review of operating system, again, we will be happy that people can will know about project. Yeah, and money for living is also important, but it's like weekend project, so it's not so important. We spend money for those strange devices. We are buying them for those money. So more money means more devices to hack. Okay, demo time. It boots. I'm cheating a little bit. And now we boot it. No, it's a virtual machine. So the E105 looks like this. So you can see the task feature screen. I can go to the second screen. I do big enough gesture, third screen, and back again to the first one. We have some nice applications like browser, which is basically, oh, it's broken. Sorry. But when you want to close the applications, you are going over the edge, same as Sailfish OS, and it's KVM, so the edge is here, and you just pull the application away. Then we have some settings up. What I have done, I probably switched the scheme somehow incorrectly. Yeah, and yeah, I have some automotive demo up. Nothing works. Strange. Let's try to fix the UI. Okay. Strange. But white theme works better. Oh, I'm not connected to internet, so that's not a good example. If you try camera on the Pine phone, it will not work. This is virtual machine, so I can redirect USB and which one is camera? This is camera. Then I can start camera on the device, and I have reached, so it works with some integrated camera on laptop, and it's problem of drivers because Pine phone have dumb camera which needs a lot of things to compute, like white balance and those things need to be computed by software. You need to control switching of resolution, because when you stream video, you need lower resolution to be able to store it, to compress it. In case of photo, you need big resolution, like you want to store 10 megapixel or something like that. So therefore, it's a difficult task, and this is done somehow with lib camera, but it's not so easy to connect it to Qt application. Or the standard video or Qt multimedia API doesn't work with that so well. So, but there are wrappers directly to lib camera, and actually in Sailfish OS they are having camera application which works with lib camera and opens door to automotive usage. So we have a lot of stack which tries to be prepared for those advanced use. We have also media player and so on. And we have that for Qt 5.15 so far, and Qt 6 will be soonish. So, time for questions. We have 10 minutes for discussion. What do you expect? What do you want? What do you? Yes.
Why do you want to use NeoMobile in automotive? Why go into automotive?
It's yeah, that's a good question. Why I am trying to use it in automotive? Well, I know that Red Hat started recently with automotive, and I wanted my talk to be accepted on DevConf, so so that's answer. Yes, please.
Could you please remind why Selfish OS is stuck on ancient Qt version?
The question is why the Selfish OS is stacked with old Qt version. I think the answer is licensing, but it is not a question on me. It's a question on Yola. So I'm not. I don't know exact reasons, but I think the license in Qt 5.6 was LGPL or something, and in newer Qt it changed to GPL or commercial. So the expensive one or that could be answered, but I'm not sure. Maybe they want stable environment because they have like big community of people. And if they migrate to new Qt, then everyone needs to update the application, which can be trouble. I'm not sure if anyone can hear me. So some other questions? If no, I hope that I will be oh, okay. Go ahead. Yeah, the question is what is how do we handle security in Nemo Mobile if we use Linux? And I didn't catch all the technologies you mentioned.
Yeah, I was talking about separation of processes.
Separation of processes, etc. So that's a good question. One of differences. One of differences of Nemo Mobile right now from Sailfish OS is that we removed some security mechanism they have. So they have some sail jail, if I remember correctly, and few others. And we are not using them, but we wanted, or we expect to implement Linux to be closer to desktop usage, like to have Linux-based security. Speaking of process separation, I don't know. One of things which Sailfish does is also, well, it's nasty trick to reach performance. They are doing, or they are launching application with which loads all Qt Quick components on the beginning and on the startup of device, and then it is using shared memory to access those components, which is pretty fast, but a little bit insecure. So we moved from that approach, also because of Manjaro's have I think fpict flag, the address randomization flag in GCC or as default. So this approach is not possible with that flag. So the answer is we are trying to move forward, to move closer to traditional desktop distributions. We are considering those options, but I think we are really not security experts, so it's hard to say if we are doing that correctly. And it would be great if someone who is security expert can tell us this should be done differently. Thank you again for a question, very good question. Go ahead, please. Yeah, the question if Selfish OS have full disk encryption. I don't know. I think yes, it is there, but we don't have it. We don't have it in our system so far, but we plan it. It's one of planned features. I'm not sure how do we want to do the decryption. How do we enter the pin code? As far as I remember, Postmarket OS does that with some LVGL tiny application which is in it RAMFS. I don't know how Sergey plans to do that. Okay, so if you don't have any other questions, I will be here on DevConf also tomorrow and also today, so feel free to grab me. I will try to do some mobile stand again tomorrow, so I will try to bring my device, the PinePhone, with other operating systems than I had before. I hope Pavel will borrow me the Librem 5 again to see other devices, and yeah, feel free to grab me, ask me, I will try to answer you, and please contribute to the mobile, fix my bugs, I need that working. So thank you.
All right, we're going to get started. So thank you everyone for coming. We're going to talk to you a little bit about a project we've been working on at Red Hat as part of the automotive program, and that has to do with managing services across different nodes. So a few things to know. I'm Pierre Chebon at Pingu. This is Michael, that I'll let introduce himself.
Thanks. Yeah, nothing more to add. Michael, software engineer at the Cow team.
We have a logo. So the Cow team is the Container on Wheels teams. You can see the logo on the top right. And because we have a logo, we have stickers. So if you have questions at the end, we'll hand out stickers. And if you stick around, we may still give you stickers if you want them. So without further ado, what are we going to be talking about here? I'm going to be giving you a little bit of the introduction of the setting up the context of the challenges for running for the automotive industries and what led us to enter that multi-node service controller. The challenges of the automotive industries are multifaceted. One of the facets that has to do with this is it's a very, very competitive landscape. There are many automotive car manufacturers around the world, and some of them are very old. If you take Peugeot, Peugeot was founded in 1810, before the first car was even created. Peugeot was originally a kitchen appliance company. They were building kitchen tools, which is also why you can still find in some places Peugeot branded salt and pepper grinder. But then, at the end of the century, they started working on their first car in 1889. And Peugeot is worth about $50 billion today. If you look at General Motors, which is the second car manufacturer worldwide, it was founded in 1908. It's $47 billion. So if we look at the number two, 3, and 4 from the bottom here, we have Ford, which is also a pretty famous and pretty old automotive company that we all know about from our history books and economic classes about the way Ford has industrialized the production of automotive. They're all about the same weight when we look at market capitalization. Then we have Toyota. Toyota is today the first car manufacturer in the world. In the number of cars produced per year, Toyota leads. And it was created in 1937. Toyota is worth about 4 times as much as the previous 3. But then we have the young king around the block, the young kid around the block, that's Tesla. Tesla is barely 20 years old. It's not even legal to drink in the US yet. And yet it weighs nearly 12 times as much as Ford that was created 100 years before. So Tesla is doing something in the automotive industry that is changing the landscape of things. It's building something that the market is believing in. And that is a challenge for the old automotive companies because they suddenly realize that, there's a kid on the block that just appeared, and it's already weighing 10 times as much as I do. And I've been there for a long time. I'm an old-timer. So that's a challenge. That's something they need to address. What does Tesla do that we are not, and that makes them at this place here? So that's something they need to look into. Something else that has changed over the last few years was COVID-19. And as much as we like that this is over, the ripples of that pandemic are still around there. And one of the side effects was the chip shortage. And we're still recovering from that. I don't have a sources for that, but I had heard at some point that during the pandemic, car manufacturers would have been able to sell twice as many cars as they did, except they couldn't produce them. They had customers, they had salesmen, they had the sales, they had the customers, they just couldn't produce the product just because of the chip shortage. So that leads to some decision that needs to be made. Something else that has changed to the industry is the user expectations. We no longer have the same relationship that we have with our IT systems as we used to. And one of the reasons is simply our smartphones. You update your smartphones. Apple is well known to be able to update the operating systems over the lifetime of the hardware. Samsung has announced a few years ago that they are now supporting the hardware for 5 years. There is an expectation about supportability. There is an expectation about life cycle for our hardware that has changed. We want updates. We want features. We're expecting that. And when you get into a car and you realize a brand new car has information in it that is maybe older that a brand new car that has been bought before, simply because car number 2 was actually started before, the program for car number 2 was started before the program for car number 1, something's wrong. I actually witnessed this myself. A friend of mine bought a fairly decent recent car, brand new, and the GPS data was older than the car which I had bought new a few years before. It's just that the model year of the car that he bought was older than the model year of the car that I bought, even though it was newer outside of the factory. So our user expectations have changed. Something else that the automotive industry is looking at is this diversification of revenue. Just being able, when you sell a car, you have no guarantee, you sell it, you have income for one time, but how can we make that income persist over time? How can I make more money from the single car? And there are a few ways that the industry is looking into all of these problems. One of them is, okay, we have a chip shortage, so we need to revise how we are building our cars. We need to revise what the onboard computing systems looks like. So this is a slide from NXP, which I found in one of the publications, which goes to what we currently have today. It's called domain vehicle architecture, domain architecture, where you have a lot of small, distinct compute units across the car. Like a modern car can have nearly about 100 different computing units. When you have a shortage of chips, you can understand that building 100 distinct compute units in a car is a problem. So what they're looking into is more what they call zonal architecture. And the idea behind that is that you have less distinct ECUs that are very dedicated to something specific and more bigger ECUs that are able of handling multiple of these discrete ECUs tasks. So you have less hardware, but bigger hardware, more powerful hardware, but also hardware that can potentially evolve over time. Hardware that is no longer designed to be exactly doing this one task, but it is produced with a design that it may be doing something else in the future. So the architecture of the vehicles are being worked on. But the hardware is only a part of the story. The software becomes the other part of the story. There is this concept called software-defined vehicle, and the idea is that by changing the software in the car, we are able to change the experience of the driver in the car. We are able to make the car evolve during its lifetime, but we're also able to customize it to the user's desires and wishes and needs. So software-defined vehicle, revising the architecture, revising the hardware is part one. Revising the software, how do we approach software in the car is part two. And then, so what's the vision? The vision ends up to be something that is very, very similar to what we have on our smartphones. We want to be able to do software updates, and we want to be able to do that over the air, just like you update your Android phone or your iOS phone just by plugging it to the Wi-Fi. You want to be able to update the hardware, while in a car it's still going to be, take the car to the car dealer and potentially get a new compute unit that is more powerful. Just like you go to your phone store and change your phone. You want to be able to have applications, being able to install these applications dynamically. This application may give you new capabilities, new features. If you look at Tesla, a few years ago there was an update to Tesla that has increased the actual engine, that has increased the horsepowers of the engines. Basically, you bought the car, it was 150 horsepower, so you update the software, your car is 155 horsepower. Simply because they were able to optimize the way the software was able to get, working with the engine. And just by changing the software, they actually changed the physical capabilities of the car. Suddenly the car is going faster, suddenly the car is more powerful. New features, new capabilities can be also something fun. So, like you've missed on paying your car's down payment this month, so the car is going to drive itself to the garage. Like, who wouldn't want that? Customization and building an experience, that's more interesting. It's like, when you're able to start to customize the experience of the driver based on the driver's preferences, which means you can build habits. And when the time comes to change your car, you're actually going to try to find these habits that you've built in your car, and therefore you'll try to build fidelity to a certain brand. So how do we get there? I've already mentioned we simplify the hardware. we also want to standardize, and that's a place where the Red Hat in-vehicle OS becomes interesting. Red Hat has been always very strong about standards and open standards in particular. So having an operating system that relies on these standards actually help developing on top of it. And then we spoke about, customization, applications. So we spoke about containers, basically. We want containers for process isolation. That's been covered a little bit this morning about being able to ensure that processes do not interact with each other when they should not. They don't impact one another. Container also means that they have a specific lifecycle management, which we're used to. So we can install, we can update, we can remove containers. And let's be honest, container is the de facto standards now in our industry, which means talent acquisition for car manufacturers become easier if they have to learn the specificities of an automotive product, but they don't have to relearn the entire ecosystems around it. When we speak about containers, we want to speak about, with an S, then we want to speak about orchestrations as well. And today, when we speak about container orchestrations, we're practically speaking about Kubernetes. So I'm going to address the elephant in the room here. Do we want Kubernetes in a car? And I already see someone say, don't spoil it. Leave the answer to other people. So the answer is, okay, I'm going to spoil it. We don't want Kubernetes in a car, and there are a few reasons for that. One of them is Kubernetes is built around the concept of eventual consistency, which means there is no guarantee when a change will be applied, but there is also no guarantee of the order in which changes are going to be applied. The extreme example that we always take, but it's technically not a good example, but it's always helped to understand, is like, you don't want to be driving a car that will say that you press the brake pedal and then suddenly, eventually your car will brake. That is not an experience you want to do. It's a bad example because we're not actually going to be involved in the brake systems, but it gives the idea. You don't want a car that is working towards a state. You want to be either in state A or in state B. You don't want to be somewhere along the journey. You don't know exactly where. Another something else is that Kubernetes is fairly heavyweight. Kubernetes and its derivative have been built around the container runtime that at that time was not able to give a status to signify when something had changed. So Kubernetes have been built around the idea of I can't get the information, so I need to go and get it. You can't give it to me, so I'm going to get it. So it's always asking like, are you done yet? Are you done yet? Are you done yet? Are you done yet? At some point, it takes resources. There was a consortium that did some investigation on that, and on the Raspberry Pi, granted it's a fairly low device, but 15 to 20% of their system resources were used by Kubernetes, just doing nothing, just Kubernetes being there and poking the container runtime, asking, are you done yet? Are you done yet? Are you done yet? Kubernetes is meant for distributed system. It's great for cloud environment. It's great for worldwide distributed system. But that also makes it a very complex system, and a lot of that complexity is not needed in a car. Things like end-demand scaling out. I'm suddenly running. It's Black Friday in the US. My store has a lot of input suddenly for the sales. Being able to scale out to a public cloud so that I can get more resources, so that I can accommodate to this sudden influx of data makes sense. But in a car, you're not going to have that sudden influx of data. The amount of data that you get from the review camera is going to be always going to be the same thing. So that scaling out simply is not needed in a car. A lot of that complexity that makes Kubernetes great in a number of environments, especially the cloud environment, just is not applicable in a car. Another example is failures. Kubernetes is designed around the idea that if some of the pod fails, it's going to do its best to keep things working. When something fails in a car, you don't want to keep working. If something fails in the car, you want to know about it, and you want to tell the drivers to take over and take over the driving of the car, put the car on the side of the road. You don't want to keep working as best as I can. Eventually, I can't detect pedestrian anymore, but yeah, that'll be all right. It's not acceptable in a car. So what do we need? We need something that's deterministic. We need to know what runs, where it runs, when it runs. We need something that is lightweight. We have a resource constraints environment. We need something that is fast. Your user expectation, when you're driving your car, you want things to work, you want things to start, you don't want to wait for things to be available. And it's a small bullet point here, but it's actually one of the core elements of what we are looking into. It's the functional safety, FUSA. The functional safety certification is basically certifying that your code is doing what you claim that it is doing. That if I ask for it to write a certain content in a file, it's going to write that content in a file. And the more complex the system here is, the more harder the functional safety certification process is going to be, because you're going to have to go through every function that are used in your code base and ensure that they are doing exactly what you say they are doing. So to answer all of this problematic, we've worked on something called Hirter, and I'll let Michael introduce it to you.
Thanks, Pierre. So, yeah, as you already mentioned, Hirter is our answer to it, and the basic idea behind it is to use systemd to control local services on one machine, but adding a thin layer on top of it, we are able to manage those units remotely. It's important to note here that we don't want to manage any state or so. We are just the facilitator of this management. And our approach here is to build a setup or a system that consists of two components, basically. The controlling component we call Hirte. That one is running on the main machine, and this one is controlling, of course, then all the connected agents. So the Hirte agent is then running on each managed node, and it gets basically the commands from Hirte and forwards them to systemd. So we are able to remotely start, stop, control units on remote machines. We decided to go here and implement this with C, considering those constraints to be as fast and lightweight as possible, and hopefully in the future to FUSA certify it. As the IPC mechanism, we chose dbus. Since it was already used in systemd, and if you're wondering now how this is exactly being set up in Hirte, I'm going to show you. So Hirte is running on the main node, which you see here on the left. It reads on startup a configuration file where we can specify, of course, all kinds of settings. For example, the port that it is listening for new connections. It then goes ahead, connects itself to the local system bus, and provides a public API to it, so that other external applications, for example, like a state manager, could use this API to control the whole system. We already implemented something like Hirte-CTL, which is similar to systemctl from systemd, but for a multi-node use case. And on the other side, we have the managed node, where a Hirte agent is running, again, reading some configuration, for example, where we have settings like the IP address of the main node. And the agent connects itself to the local systemd dbus via Unix domain socket. And by this, we are already able, in the agent, to control services on the managed node. But the agent then goes ahead and wants to connect itself to Hirte based on the settings that we specified. Namely, it issues a connection request over TCP/IP, and Hirte itself responds by creating a peer-to-peer dbus. This peer-to-peer dbus is used exclusively between Hirte and the respective agent. More on that later. In addition, Hirte does a lookup. When the agent registers, it does a lookup and checks if it can find, for example, the node name. And if it can't find the node name, it rejects the whole connection request. If it can find it, then it accepts the connection. With that, we are already able to control those units on remote nodes. And of course, we can scale up, so from 1 to n nodes, which we all specify upfront in this configuration file. And as you can see here on the left side, on the main node, we can of course run the Hirte agent alongside Hirte with basically the same mechanism, of course. One question that might already arise is, how do we deal with cross-node dependencies? Like in this example here. Consider we have this setup. On the left side, we have a node new foo. On the right side, a node bar. And both are connected to Hirte. And now we want to start the cow service on the node foo. What we don't know yet is that the cow service requires the sheep service to run on the node bar. Well, how could we resolve that kind of dependency? For once, like I said, we could use an external state manager that basically uses the Hirte API, but already knows that the cow service requires the sheep service. So it would first start the sheep service, wait for it to run, and then start the cow service. What we added, however, was a feature, the so-called proxy feature, to push this dependency resolving to systemd, that a developer could, at development time, define, okay, I need the sheep service to run on node bar for the cow service. And it works roughly like this. You see here on the lower left side that the cow service requires a so-called template unit. This is a unit file that Hirte provides to the developer, where you can pass in the tuple after the add symbol for node underscore the unit. So you specify the name of the unit that you require and the node that you expect this unit to be run on. In our case, we want to have the, and that's actually a mistake. It should be the sheep service here, so it should be like Hirte minus proxy at bar underscore sheep service. Please substitute that, which this template unit then takes and passes it to a small binary, the Hirte proxy, which in turn separates those two input parameters and does an API call to the Hirte agent. It's important to note that this API call is blocking, so the proxy waits for the whole flow, so it can distinguish between a successful or a failed setup. And therefore, this can reflect then, of course, in the cow service. The agent forwards that request to Hirte. Hirte knows now on which node to run which unit. So it creates a start request on the node bar in our example. And it wants to start another template unit. We don't want to start it directly because then we cannot, because then we kind of limit the ability of the developer. By using a template in between, a template unit in between, the developer has all the freedom to specify and define the sheep service however he wants it to run. This template unit again then has a very weak dependency on the requested unit, meaning if it's not already running, we will start it, but if it's already started, then we don't care. Nothing happens basically. Important to note, however, is that Hirte will keep track of all the references on the node unit tuple, so we know basically how many references there are. And with this setup, we can already resolve this dependency just by using already existing systemd features. And of course, we can do so on development time, so to say. Yeah. After this, and now I have a few examples that I can show you, which I pre-recorded. First of all, for these examples, I used this setup. I started a Raspberry Pi and had an Hirte agent running on it. And I also ran a Hirte agent on my laptop, connecting both to Hirte, which was also running on my laptop. I was interacting with the system by using our built HirteCTL. And well, the first thing that comes to mind is listing all the units that are on those nodes. So in this example, I queried for all nodes the units that are running or not running. And I filtered them based on their name. In this specific case, I wanted to have all units with the name that contained a bus in it. So we see, for example, the bus service and bus socket on the laptop, which are in an active state and are running. But we also see, for example, some devices that are plugged. We can also start and stop systemd units. In this case, I first filtered, of course, for the specific cow service that I wanted to start. And we see that is currently in an inactive state and dead. Then I started the cow service with HirteCTL start on the Pi cow.service, and after querying it again, we see it's active and running. Again, stopping, same procedures always. Stopping it, HirteCTL stop Pi, cow.service, listing again, and it's inactive and dead again. When starting this cow service, I created beforehand a monitor. So you can imagine those start and stop operations always involve some state changes internally on systemd side. So what if we want to get notified on certain changes? We can set up a monitor with, for example, HirteCTL monitor, and I wanted to get all units on the Pi. And this cut example, because otherwise it got too large, just shows the state changes between the states of the cow service. So you see in the second one, you see that it currently had an inactive state, then it changed to activating, and finally it reached an active state. And of course I could now probably do some different operations if I need to. And the last example is kind of similar, which is HirteCTL monitor node minus connection. So as the name basically suggests, we can also monitor the state of the nodes. In this example, you see that the laptop and the Pi were online. Then I went ahead on the agent, on the Raspberry Pi, stopped the agent, and this immediately got reflected on this monitor, so the Pi was stated as offline, which is especially useful if I want to health monitor my system and do some, well, operations or have some fallbacks based on it. Yeah, and that's already it. Some questions, yeah.
First of all, I don't really understand what does so different from systemd. Why not just extend systemd?
So systemd already has the mechanism to do remote connection, but one of the systemd already has a built-in mechanism to do remote connection, but that remote connection relies on SSH. And SSH is not something we want to be running in the car because SSH can hardly be limited in the scope. So you have it gives you a full shell section, which means if someone plays around in the car and gets a shell access to one of the compute units, it's not actually something we want. And by using the Hirte agent and the control, we are actually able to expose in one port only the management to control services. You won't be able to install a rootkit by this because you can only control systemd services. The other problems, so that's part one. The other question is doing this in systemd itself is something that we've been thinking about. We would love to be able to have it in systemd proper, but there was a timing perspective. Being able to work with the systemd community to polish it and make it up to the systemd standards would probably have taken more time than we have available to get this project in a state where it's usable. So I would still love to see that happening, but we also needed to figuring out, is this what we wanted? We started with proof of concept. We talked with the car manufacturer that we're involved in. Does that satisfy your solution? Do you see things that are missing? This presentation is still something about us trying to figure out, are there things missing? Are we missing something in the picture here? Did we forget something? There are always more brains in two heads than in one, so there is always a capability that we have seen something. And if we were to implement that in systemd, then we would not have the flexibility about potentially, changing our approach if we needed it to. So that will be my questions. We needed to validate our approach. We cannot use SSH, and doing it in systemd proper would be ideal, but we're not there yet.
Okay, for example, dependencies that you run, you just check for at the moment, I think, for the service running or not, and you do that through systemd. But can you use the full-fledged systemd dependency tree, check for versions, files, databases, whatever that is running?
So the question is about leveraging systemd for dependency resolution, and it's exactly what we want to do. That's why we've implemented the proxy service, because we don't want to have to deal with figuring out the order, what can I start in parallel, what needs to be sequential, and systemd already has all of the logic and is built for that. So we actually want to leverage as much of systemd as we can, and we try to complement it rather than re-implement it. Yes.
How do you really use this anyway right now, say in a specific project? And let's say what benefit do you get out of it in terms of, I guess that you don't want to use Kubernetes because of the footprint, and maybe it's like the logic behind how it's a state is a little different than systemd itself. So do you have any specific kind of project that this would better, let's say, in automotive industry, that this has, let's say, more kind of pros rather than cons compared to Kubernetes, just to understand? Because I know that systemd also is going in the direction to be an orchestrator for containers. So you might think about this kind of chains. So you might also be able to pursue the systemd as a project, let's say, on top of it, and not really very well about this direction of managing containers with also systemd.
The QM, right?
I'm trying to see if I understood all the question.
So basically, there is a use case, and then whether you decide to go for the systemd kind of as well. I think those systemd also at some point already made orchestrated containers around systemd. So we can resolve the part of dependencies, while as part of like shows, as part of the hardcore specification. This is the reason, and whether it's a use case that we have applied this kind of technology.
So basically your question is if we already have a project where we applied Hirte, or
yeah, but whether like this project you start with Kubernetes and then you decide to change or like implement your solution on top of systemd.
So did we start by considering Kubernetes before we implemented it? Yes, we did. But we built the analysis that I have presented earlier. We did the analysis that I presented earlier and figured that despite a lot of people asking us, we want to run Kubernetes in the cars, we conclude that Kubernetes is a great tool, but not to run in the specific environment that the car is. Because it's complex, because it's heavyweight, because the complexity is going to make the functional safety analysis practically impossible, because it has the eventual consistency that is built around. So all of these make it like, it's not suitable for the in-car part.
I think some key that here is saying is Kubernetes aims for eventual consistency. We definitely don't want that in automotive. We want things to be very deterministic. That's why we want things like real-time harmonies and such.
Well, even the systemd is right. Like when you have like, let's say, premise service you have it will drive, real halo itself. So in some way, it does, the controller does,
the things that, and I think it's going to have to be the last question because we're out of time. One of the things that Kubernetes does is that it's very hard to impose Kubernetes run certain payloads on certain systems. And in the automotive world, you need to be able to test the entirety of your system in bench, in silico, in bench before you actually start in the car, so that you cover all of your bases when it comes with I have a critical system that I need to ensure that this critical system always have enough resources. And then the question of the dynamism of I want this container to run wherever there are resources is actually something that is being considered, but we don't have an answer. We don't have a proper answer for it yet because we still need to ensure that adding an extra container, on a specific system is not going to interfere with critical systems that are already running in there. So there is the environment, the in-vehicle environment can be a lot more static than what Kubernetes is used to deal with, and they are basically built really for different worlds, and it's going to be hard to make Kubernetes work for alternative use case. But I think we're going to have to stop in here because it's out of time and the next speaker.
Yeah.
We can finish outside. Right? Yeah. Okay. Thank you for that.
Thanks.
It's a bit difficult to pronounce. I've been a software engineer for 6+ years, but I've recently transitioned into the cloud native space, like sometime this year. I'm also a DevRel engineer at Spectral Cloud, and I also contribute to the Kairos team. So today we're going to be talking about Meet Kairos. I mean, for those who have already seen us at the booth, Meet Kairos again, the meta distribution for the edge. So when we talk about meta distribution, what do we mean? We understand that different teams use different Linux operating systems. For example, Alpine, OpenSUSE, and Fedora. And we do not want to reinvent the wheel. I mean, all those operating systems already do a great job at providing great package managers and everything that they do. So we don't want to ask you to change your operating system. So, and we also understand the fact that companies have invested so many years into learning how to use these operating systems. So Kairos is not asking you to change any of this. Aside that, different organizations have licenses that they use, and you don't want to do away with that. There are also, for people that don't have licenses, you might have golden images. And these golden images, like some of the templates and the standardization that your team makes use of, you don't want to do away with that. So that's not what Kairos is asking you to do. Kairos actually builds on top of what you have already. A lot of our computing is moving to the edge, which means that we want to move away from centralized data centers and then move our workloads to closer to the customers or closer to our clients. And for real-time processing and all the advantages that the edge provides, we are gradually moving more to the edge and then less towards data centers. So because our devices and our workloads are moving closer to our customers, there are a lot of challenges that this comes with, and some of these challenges include security. I mean, so when your computer is, or when your computing is closer to the customer, there's increased vulnerability. It can be tampered with easily. And there's also the case of stability. So if a user wants to make an upgrade or make an update, you want the user to still be able to make use of that edge device without having any issues. So the case of stability also comes in. And then there's deployment, right? Everybody wants a plug and play. Nobody wants to go through all the deployment hassles. And like companies also want you to be able to like have very easy deployment experiences. So these are some of the issues that come with having your devices or your computing closer to the customer or in the edge. So Kairos to the rescue. So for security, right, one of the ways in which Kairos solves this problem is by immutability. This means that all the OS components and like including the kernel and init RD are immutable. Like you can only read, you can't write. However, Kairos also provides like a persistent, like where you can persist your data and you can always update this part of Kairos. And then when you think about it, the first thing that comes to mind is, okay, does it mean that this other part can be tampered with? And that's not the case. Kairos actually provides security by encrypting this user data part, encrypting it in TPM chips, and this means that if for some reason your hard disk, for example, is stolen, you cannot, decryption cannot happen except on the same computer that, on which it was encrypted. So the user actually needs your physical device to be able to decrypt that data. So Kairos provides this security both on the OS level and then on your persistent volumes. And then for stability, Kairos also provides alpha beta upgrades. And what this means is that you have your running image, which is your active image, and you want to make an upgrade to another like make an upgrade. And then that upgrade that you want to make, we call it the passive one. So Kairos downloads the newer image that you want to update to. And there's a transition phase where after the download, Kairos tries to reboot your device and then loads the new image which you've downloaded. And if there's any issue, it's going to switch back to the previous image. And this is how it provides stability. So I'm going to allow Mauro to continue from here.
Yeah, and of course, even if we try to make everything as simple and resilient as possible, we know as engineers that bad stuff can happen, right? For those scenarios where for some reason neither the active or the passive image is working properly, we offer also a recovery partition in which you can have a shell and try to either fix one of those two images that is broken or at least get a hold of your data and save it, right? Another interesting feature that comes with Kairos is what we call a peer-to-peer network with self-coordinated cluster bootstrap. What does this mean? Well, there's this component that we introduced called Edge VPN. It's basically a mix of a VPN ledger, and what it does is that every node that you install with this component is going to keep record of every other node which you provided with the same kind of key. And these nodes are running on top of the live peer-to-peer library. That means that if for some reason there is limited connectivity, some protocols are not working, you can make use of any other protocol that the live peer-to-peer library offers. This can be useful because some of the edge locations, might be restricted in the kind of connectivity that you have there. So I don't know, if for some reason TCP is not working, maybe the WebSockets are available and the nodes can continue speaking to each other there. And another way in which this is useful is, let's say that I want to install a cluster and I decide to have, for example, 2 master nodes and the rest can be workers. But of course, one of our master nodes stopped working for some reason. Then what happens is that because every node has the ability to know about the others, then they will start to communicate between each other and with consensus decide, you know what, we lost one of the master nodes, so now I'm going to become master node and again update this ledger that each of these nodes had in its own, so that at the end of the day you continue having the stability. In this case, for example, if you want to provide high availability on that particular cluster. Of course, if at some point that other master node comes back online, he's going to be able to talk to all of them and again decide whether it stays as a master node or if downgrades as a worker. What else? Another thing that we want to do, like we were mentioning, is make it easy to deploy. And one of the things we provide here is that Kairos is easy to configure and maintain. What we use right now is Cloud Init for the configuration of those nodes. So all your configuration can be done via YAML files. That means that you can keep it in your GitHub repositories, keep track of the changes that configuration is having throughout time. And as you can see here, this is of course a very, very simple configuration, but you can get an idea of how it works. You just have, in this case, the number of users that I want to install. I want the user Kairos is going to have the password Kairos. And also on top of that, I'm going to tell that this user can get the GitHub SSH key from the user called modeler, and also maybe an SSH key that I provided there. And finally, in this case, for example, I'm enabling the use of K3s. So that means that this node will have the full API capabilities of a Kubernetes cluster. Another way in which we try to make it easy to deploy is that we provide a web interface so that the only thing that you have to do is, if you know the IP of one of the nodes, you go, in this case, for example, to that IP and the 8080 port, and you will see website where you can just copy-paste the configuration that you want installed for that node, and then you run it, and by the time it's done, your system is going to be configured to the like of that configuration. Some cases, being at the edge, you have some particular scenarios. Maybe the person that is in physical possession of the node doesn't have, you don't want them to have the full configuration of the node itself. And in those scenarios, what we provide is that as soon as the machine is booted, it will show a QR code, and then the person just needs to take a picture. Then they can send this picture to your headquarters or however you're doing this, and the person in the headquarters is going to, with the simple use of a CLI tool, in this case the Kairos CTL, is going to register that node. And it's going, as you can see here, I'm going to provide what is the configuration file that I want and provide the QR code. And just by that, I don't need to pass an IP or anything else. It's going to know how to connect to it. Another interesting component that we provide, also useful when you're doing deployments, is something that we call Aurora Boot. Let's say that for some reason you want to send a couple of clusters to different places across the country to build these clusters in I don't know, different parking lots or grocery stores, whatever it is that your business is, right? And, but you don't want to go send a person, do the full configuration in the place, and then go back. It could be very expensive, or it could take too long. And for that scenario, what you might want to do is do some net booting configuration. You just spin up Aurora Boot, and then as you tell it which image you want to install, again, which configuration you want for that image, and then every machine that you start in the same network is via Pixie Boot is going to be configured to have that specific setup that you set for it. Then, of course, you just unplug all those devices, put them in boxes, and send them to the locations that they need to be. The next time that they boot is going to be with the proper configuration that you were expecting to have. So, do you want to? So, to finalize, we think Kairos is a great solution for edge computing because, just to summarize the little things that we mentioned right now, it's immutable, and that means that we reduce the risk surface that an attacker will have. It's distribution agnostic, so we allow you to continue using your existing knowledge on whatever main distribution of Linux that you are using. We do AB upgrades so to facilitate and to avoid ending up with a system that is not working after an upgrade. We have TPM encryption to add security on the user data that you have there. We have peer-to-peer networking so that communication between the nodes is as easy and simple as possible, and as reliant as well because of the peer-to-peer library. And finally, it's easy to configure and maintain. And last but not least, let us do a quick demo. I would have loved to do a live demo, but you know the risk of this not going properly, right? So instead, I decided to go for a video. I'll move this so that you continue listening to me. And what we're going to do here is that we're going to create 5 nodes. And these 5 nodes all together are going to become a cluster, a Kubernetes cluster. And I will be skipping because you don't need to wait for everything that is happening. And then once I create those machines in my data center, I am going to spin up Aurora Boot. Here, you can see that Aurora Boot can be run from a container, or you can install it on your machine. And I'm going to pass this YAML is the configuration YAML that I was just describing before. It has K3 as configuration, and in this particular case, I also mentioned that I want to have 3 master nodes from the 5 machines. And that's it. We let it continue for a bit. And what Aurora Boot is doing right now is it's downloading an image from the cloud. This can be one of the images that we provide or one that you built with Kairos. And it's going to copy the rootfs into your local system or in the container, depending on which of the 2 versions you used. And the final result that it does is an ISO image that will be delivered via the Pixie Boot via the network. And now we're going to start spinning up the VMs. So you can see here we can start them in parallel. They are all in the same network, so they are all going to start getting the same configuration. And I'm going to launch a remote console so that we can see what is happening in the node. Here on the left, you see Aurora Boot receiving already all those connections from the different VMs. And that smaller window is the VM that's spin up, and it's already receiving Aurora Boot instructions on how to configure and install this node. And let's make it go a bit faster. That way there's more room for questions. Yeah, we open consoles on all of them so that you can see that everything is happening in parallel. You don't need to wait in serial for each of these to be configured. Let's go faster. This part is a bit slow. Yeah, and you can see that one of the nodes at this point is already booting. I think I went a bit too far. Yes. So you can see that there is grub, and it's a bit small maybe, but there you can see that we have the option to just boot Kairos, to go into the fallback, which is the description that we were saying about the AB upgrade. So if there's some issue with the current image, you can fall back to the previous one that was running. The recovery one, in case the 2 A and B are broken, so that you can try to fix things. And the rest of the nodes, of course, are also going to start booting at some point. And here in this screen back here, we can see that Kairos already booted for that particular machine. So now what we're going to do is we're going to SSH into one of the machines, and using the Kairos agent inside the machine, we're going to fetch the information on how to connect to that cluster. So for that, what we use is a command called get kubeconfig, and this gives me all the information of that configuration, which then I could either, all of these images come with K9S as well, so you could do it from that node, but just to show you that I also can do it from my machine, all that needs to be done is copy that configuration, save it locally, and then point our kubeconfig to that configuration. Then we start K9S. It's going to communicate with the cluster that we just spin up. And now we can see it there. And next step, we can see how we have 5 machines. The 5 have been registered in the cluster. 3 of them, the first 2 and the last one, are masters, like we defined, and 2 of them are workers. And just like we can do anything that can be done at this point with a Kubernetes cluster, like showing up the pods and see traffic there, or any other service, kubebip, anything like that. And that's pretty much for the demo. As you can see, it's relatively simple to set up a complete Kubernetes cluster on your edge devices. So now I would like to give you guys time for questions. Is there any question out there?
So these images were mutable, right?
Sorry?
These images were mutable, right?
These
Immutable.
Immutable. Yes, you're asking if the images are immutable. That's correct. So what we make is that the root partition, so and all your configurations, like everything under etc directory and all of that, is not going to be able to be changed because it's mounted read only. Yeah, and on top of that, like so what some distributions do is that they create the init ramfs at the moment of doing the installation, and the problem with that is that during that step you could be at risk. But what we do is that we create the init ramfs at the moment of building the image. So at that point, you're still within your network, right? Within your safe environment to a certain degree. And once you have it installed in the system, even the init ramfs is read-only, and same thing for the boot partition. Anyone else? Yep.
I saw Ubuntu and OpenSUSE in there. K3S is a branch of project, right? So I guess there's a Ubuntu, OpenSUSE. Do you also support this with Red Hat family distros?
Yeah, at the moment sorry, I'm going to repeat the question. So which flavors or which distributions are supported with Kairos? And at the moment, we have, as you were mentioning, Ubuntu. We have Alpine Linux. We have Fedora. We have Rocky Linux. Yesterday, someone coming to the booth asked me if we could make it work with Alma Linux, which is very similar to the Red Hat family, as you were asking. Turned out just changing 2-3 files very simply made it work there. So I thought that was pretty cool. Red Hat, yes, but of course with Red Hat you're probably using licensing. So then there's this additional step that you have to do, but is basically supported since we have Rocky Linux and Fedora there. Yeah. And we're happy to try to introduce more distributions if people are interested in them, of course. The basic requirement that we need is, right now, our two types of systems are systemd and OpenRC, and ideally glibc, but of course, for example, with Alpine, we only get access to Musl, so it will really depend what your distribution offers for us to do the transition. Anyone else? Well, if it's not the case, then thank you very much for your time. And if you have still any other questions or you want to try Kairos out, we have our website where is all the documentation and the different image matrix that we support. There's also our GitHub repository. We also have Matrix and Slack channels where you can make questions. And finally, we have office hours. We meet at 5:30 every Wednesday European time. So if you just want to pop up, say hi, or tell us what is missing in Kairos, please do, and we'll be happy to try to make it better. Thank you.
you for joining us again in DevConf. Now we will continue with another session, which will be led by Pavel Picha, who comes from Czech Technical University in Prague. Enjoy and welcome.
Thank you for introduction, and good afternoon to ladies and gentlemen here or on the stream. My presentation refers to our long journey through the work on CAN and real-time and so on. So it is quite dense, and if you have more questions and want to know more about specific project and so on, then please take the contacts and contact me later and so on. All the hardware and software which we have built for this area is open source, or you can find documentation for it and so on. So you can reuse the code. And the content of today's presentation is some short introduction what it is CAN, who knows what it is CAN and how it works here in the about arbitration, CAN FD. Oh, I have make very short this introduction because I expect that there will be more people who knows a little more about the CAN. But anyway, I try to introduce the technology, and then I start to speak about our own work in this area, and then about our interesting open source project of CAN FD controller, which can be even implemented in the FPGA or in the hardware. There has already been some attempt to go through the synthesis in the hardware, and then I will speak about real-time and latency testing. So for the introduction, as you know, probably CAN has been introduced in 1983 by Bosch company, and the main goal for this communication, packet-based communication, was to somehow simplify the wiring inside the cars, because today you have so many signals that you will have thousands of wires coming from one position to another to switch something on and off, and they decide to multiplex it on the wire through the packet communication. And initial CAN 1.0 design allows us up to 2048 identifiers, which can hold, each can transfer up to 8 bytes of the actual information. So in the fact, 64 single bit yes and no signals. So for example, into one message you can distribute all the switching of lights of that day standard car or vehicle. Today, when you have dimming and back channels for measuring of the voltage on the lights and diagnostic of profiler and so on, you can find that even those 2048 messages is not so much. So they extended the support to 29 bits in 1991 in CAN 2.0. And what is interesting on this communication is that it has a deterministic media arbitration, which is based on the ID priority. So as the message has lower ID, it has higher priority. And okay, I have skipped this in my presentation today, but but it works such way that basically at each bit which is sent from the identifier, there is a running wired AND function, and that station which sends a given bit with a low value 0 wins, and the other ones stops sending a frame. So this way it is ensured that only one station succeeds and send the desired frame on the bus, and even that one which abandons the sending can receive a given frame. This solution of the base collision avoidance or resolution it has its price, and it is that the signal has to be distributed through a whole wiring forth and back to detect the collision deterministically. So it has a disadvantage that at this phase we cannot speed up communication above some limit. For example, if you decide that in typical car single bus network or single bus channel doesn't exceed 30 meters, then you can go with the communication frequency up to the 1 megabit per second. But you cannot go faster, because in such case you cannot resolve the collision, because there is some time when the signal is distributed through the wires. Okay, so this is the price, and this means that the throughput is not so great. So then there has been provided a new version, extended version, which is called CAN-FD, Flexible Data Rate CAN, which uses slower communication with a deterministic resolution only for the sending of the ID of the message, and then actual data are sent at the higher bit rate. Typically in today's cars, the CAN-FD frame can send up to 64 bytes, not 64 bits as the previous version, and usually it is used with 500 kilobits per second for the arbitration phase, but during the data transfer phase, the frequency or speed is increased to 2 megabits per second, or in theory it can be even 8 megabits per second, but in automotive usually 2 megabits per second are used. So basically the arbitration is run at the low speed, then we switch to the data rate inside the middle of the control field, where is the information that now is the switch. Then the actual data are running at that high speed. Then there is a quite precise cyclic redundancy check field, which ensures that corrupted messages is spotted, and that there is no possibility that, or very low probability that we consider a corrupted message as correct. And then there is an interesting field which is run again at the initial speed, and it is used for the confirmation of the correctness of the reception of the frame. So in theory, if one of all units finds that there is a problem with the frame, then this unit sends a NAC, non-acknowledged field, and this way ensures that no unit considers the message as correctly transferred. So in theory, you should have all units in the scenes with global view of the messages and so on. So it is big advantage. If some unit misbehaves, then it automatically counts that it is necessary to disconnect it, and basically it falls into the passive mode and so on. So, as we have seen, CAN-FD extends the data field to 64 bytes. Then today there is an extra long version which allows to sending up to 2 kilobytes and 48 bytes in the length messages, which is used to encapsulate even the Ethernet traffic inside the vehicles onto the CAN network in the vehicle. It is question how much it will be used, but it allows to switch to even faster data rate, which is symmetric, up to 10 megabits per second, and it limits the actual part which is sent at that low bit rate for the arbitration to really a minimum to allow the resolution of the priority, and then the rest is sent at high speed, high bit rate. And even the IDs are not sent during the arbitration now, but they are move to the fast field. And the arbitration is only 12-bit at this time. Okay, the support in the Linux systems, because Linux are used today for industrial application, for automotive, and so on. And the first implementation was different vendors provided drivers for CAN, and those has been usually integrated as a standard character device. We have started it in 2003 at our university to build some Lincoln driver, which was vendor neutral, and it was part of some bigger project of open source components for real-time application, and it has been used at some companies up to 2018. At least at 2018 I have get some feedback and support requests and so on. And it was character-based, but because CAN is in the fact a networking standard, then Volkswagen, together with Pengutronics company, started development of the socket CAN, which is socket communication-based interface to the CAN hardware, and okay, so you can use typical select and bind and so on the CAN network, even that it is a little special because the concept of addresses is not so clear, or so is a little different from the standard TCP/IP communication and so on. And this solution has been accepted at 2008 into the Linux mainline. We have helped in this design with computation on bit rates, and some another people converted parts of our Lincoln support even to the socket CAN. And if I return back to my first experiment with CAN, we have built some ISA bus card in 1997 for our RS-485 communication without instruments, but we have added there a block to allow to communicate even with a CAN. Then when we have built our motion control system based on Motorola 68376 chip, which has a tau CAN controller, then we have started to play with the CAN. Then at the university, we have more PC104 system for that Osera project, and we have developed a Lincoln driver based on it. Then we have ported it to the PCI CAN from Quasar and to the cards from ESD, and it has accumulated support from many different hardware and contributors and so on. We have even implemented drivers for Unicontrols company, which use a VME-based system, first based on OS 9, but when the support of OS 9 was terminated, they switched it to the Linux. They look at the Linux as a childish toy and loud as us when we speak about the CAN and Linux and so on, but when they cannot use anymore OS 9, then they have been very happy that they have a support and they use our Lincoln in the railway vehicles and other applications for many years. Okay, then we have attempted to build a converter between the USB and serial and CAN communication, and for this we have already built Lincoln support and then even a socket CAN drivers. Then we have worked on higher levels of the CAN communication, which is, for example, CAN open standard, which is standard how to map parameters and service object to some numbers and indexes and allow to maintain industrial drivers, motor drivers or I/O extenders and so on. And we have built this system such a way that it was quite generic, because for each device which can open protocol, so it is that protocol above the basic CAN layer, you should get electronic data sheet. And we have decided that we will build a general purpose device and library which can read this data sheet and mimic actual hardware. So for example, we have some Vago I/O terminals which can open. So we take the data sheet and run our virtual device. Virtual, but not so virtual. We will see later. And there is a state machine and some actual interface to the drivers. And our driver solution was done such a way that it can connect to Nutix, Lincoln or Socket CAN drivers, and this is how it looks like inside the CAN open device. So basically, there is some object dictionary which is described by the EDS. So for example, there is where to read how many I/O ports are available on a given device, ability to access actual I/O ports. Then it is possible to map those objects to the process data messages, which is very interesting, because on CAN open, basically actual process variables can be transferred without any need of overhead. They are basically sent directly in the raw CAN frames, because it is possible to allocate for them ID, and then through this mapping, there is a generic mechanism how you can map different bits from different variables to the actual location in the process messages. And our library allows to interface with different CAN drivers providers and standard on Linux, or even on a small microcontroller-based devices. And because we want to connect it even to the hardware to mimic the whole device completely, then we have allowed to load dynamically libraries and describe connection between those objects which are used for the communication to the actual real hardware, and we have an I/O device built this way. And we have built a device which, or software which allows to monitor such network, which allows to communicate and set different parameters and makes, in the fact, a gateway between the TCP/IP communication and the CAN open communication. And we have provided a Java-based monitor and Qt-based monitor for this. And we have there a demonstration, for example, of I/O module, when we have used Linux Comedy drivers, which allows to connect to I/O devices. So basically, really, our virtual, it is a question, software can operate exactly the same way as a standard PLC controller, which is providing this functionality of CAN open extender or I/O device. And we have written even Comedy drivers for some hardware from some data acquisition cards, which has been released by one Czech company, and those drivers has been accepted to the mainline. So I skip this, or will skip this exact example, because it is quite complex, because we can even emulate a whole Z system inside a QEMU. This is the way how we can access from the monitor different variables in this system. We have there even example how to run a profile which allows to control brushless DC or permanent synchronous magnet motor, steppers motor, and so on. And all this can be done with our libraries and connected to the hardware and so on. Okay. Then started our attempt to provide a or first attempt to implement a CAN support for RTMS, which is a real-time executive for multiprocessor systems, which is designed initially for US Army and now is used by European Space Agency and NASA. But when we started work on the CAN in this area, there was a problem that there is not a common hardware. So for this reason, we have started a Google Summer of Code with one of students and implemented at the end the QEMU emulation of the CAN hardware. So today you can run a standard QEMU because it has got into 2018 into the QEMU mainline. So you can run a standard QEMU with standard Linux. You can specify when you start a QEMU that you want to have there a PCI-based card in your ARM or MIPS or x86-based system, and drivers automatically load and allows to interconnect a CAN bus inside that QEMU. So basically run there the software of some engine control unit or something like that, and connect it with external hardware and external world through the drivers and real hardware to the standard bus. Because at our university or faculty, there was a strong group which support CAN for Unicontrol, Škoda Auto, Volkswagen, and build the test equipment for this area, which needs not only to have the access to the network, but needs even ability to alternate the actual frames and inject the errors and so on. So you cannot use a third-party fixed silicon for this. Then there started a project by Ondřej Ile in 2015 to upgrade these designs for CAN FD, that extended version. And at that time, I was done at my company a consultation for one Volkswagen subsidiary with their FPGA-based Zinc hardware. And they want to connect it to multiple CAN buses and found that it is a big problem to get MCAN licenses from Bosch. And that MCAN core, which is standard CAN FD core provided by Bosch, is too big that it doesn't fit into their FPGA in the number of channels which they need. So at that time, I have started the project and negotiated that the subsidiary of Volkswagen bought the design, which has started as that experimental tester design at the university, make it open source, and paid for adapting it for their specific needs. And this is how CTU CAN FD core has slowly developed into the full-featured CAN FD controller, which is fully described. You can find the sources, and it allows to work with FIFO on the input, connect to the socket CAN between from 2 up to 8 TX buffers to send the frames to the network. And it is implemented such a way that it can be connected to the AXI bus on some Xilinx Zinc FPGAs, or it can be connected to APB, to HB. There was even an attempt of some people and contributed connection to Litex, which is now used in the hobby project with FPGAs. And this design has included even some advanced features for the testing. So, for example, bus monitoring mode and restricted operation mode and so on. So it is interesting even for such applications. When we finished the project for Volkswagen, then Ondřej Ile, who is main author and at that time a graduate student at our university, continued on the project on his own time and built a complex infrastructure to allow full testing and basically get very near to full compliance. Or in the fact, we think that we are compliant, but we do not have enough money at this moment or need collect too many money to ask for the real real certification. So it is waiting for some group of people, companies who has interest to join forces and resources for this. But we have our own tests which are mostly, or which are passed by this. Okay, and because we want to have even emulator, then I have run bachelor thesis with one of my students, and we have implemented emulation of our own CAN-FD controller, and it is now part of the mainline QEMU, so you can connect even the hardware through a CAN-FD and run in the virtual environment a whole engine control unit and so on. And we have support for Zinc hardware. Those are our education kits for PCI Express FPGAs from Altera, Cyclone Nano. There has been some third-party attempt to connect it to Litex. It has been ported even to some space-grade FPGAs and some diagnostic tools and so on. One of our students has used our design as a basis for his own testing of the open source toolchain to transfer a design to the silicon and so on. Unfortunately, we do not have money to get the silicon yet, but we have got even some offers. There are some companies which has done this as exercise, how to get it into the state when it can be run on the ASIC. And we have even fault-tolerant version, which is used in the space already. And when you run some communication or you care about a motion control application or something like that, then you need to ensure that your latencies in the system do not damage the stability and safety of your control application. Maybe you can know OSCDL quality assurance farm on real time, which is a very good service, which provides a precise testing of the fully preemptive kernels and standard kernels, but for standard Linux kernel, you cannot expect anything. There can be a millisecond, 10 millisecond latency if you plug USB or HDMI cable and so on. But for a fully preemptive kernel, we have been able to run our CAN stuff and some control application up to 30 kilohertz with no detected misses of the sampling. So you can see this is some slow ARM Zinc. In the fact, this is I have took from their farm the latency plots for this hardware, which I have here. And they do the testing for a long time. So their long-term testing through the many years shows that well-maintained, fully preemptive kernel can achieve, okay, you cannot do a mathematical proof that there will never be a longer latency, but you can see that in this logarithmic scale, if there is a single overshot of the latency or jitter bigger than 100 something like 20 microsecond on this hardware, slow hardware, then you will spot it. But we have decided that it is necessary to provide some such guarantee even for a CAN communication, and because our system allows to measure even up to 10 nanoseconds the times of arrival of the frames and so on, we have decided that we switch our older attempt when we have done some assessment of CAN-FD gateways and drivers infrastructure and system calls for a Volkswagen, that we switch it to our new hardware. And it was task of one of my students who has finished the thesis last year, Maciej Wasilewski, who added the timestamping into our driver, and follow-up by bachelor thesis of Pavel Hronek has finished in the latency testing on the web system. And basically we send the CAN message on one bus from one system. We receive it by the second CAN-FD channel, which precisely measures the time. But then there is a device under the test which receives the cane frame, and only functionality is to go through the kernel or even in the user space and send it on the other bus. And then we measure the another time. And this way we can exactly measure a duration which is caused by the latency inside the drivers and Linux kernel and so on. And this is the test system which runs a daily test of a mainline Linux kernel and on the real-time patched version of the kernel. And this is overview. We can do the latency inspection of individual runs and see latency plots. We have there this heat map, or we can see again this long time plot where we see latencies, how many messages basically exceed a given latency. You see that there are still some mirror problems. And it runs each day, and you can find materials for our work. And okay, in this area, but I work even on some project for European Space Agency for real-time control of different devices. At this moment, on the roof of ESA in the Netherlands is running our motion control to track some satellites and so on. So, okay, so it is all from my side. If you have interest, take the leaflets, ask. I can even demonstrate something for you here. We have included in our design even the logic analyzer, so we can see the signals on the real bus, on the virtual buses, down to the 10 nanosecond resolution and so on. So, okay, thank you for your attendance, and if you have some questions. Yes, we have work. Okay, question is if we have work on the security issues with the CAN. We cooperate with Oliver Hardkop, if you know him, from Volkswagen. He is behind the start of Socket CAN, and he has designed a message authenticated CAN variant, and we have done the second implementation. So they done their own, and we at the university has done the second one to prove that there is possibility to do the interoperability. But it was at CAN days, so it was based on that 8-byte messages, which makes the thing quite tricky, because it was necessary, basically it works for short messages, it was possible to provide the cryptography directly with the signal in the 8 bytes. But for the longer messages, it works such way that message has been sent, and if the receiving unit react on the message, but then later didn't get the information that it was correct through the another message, which has a signature, then it basically need to abandon the functionality or signal that there is a problem. But usually, if you have this latency, something like 10 milliseconds or something like that, then reacting on the incorrect message for so short time is usually not a problem. So, and today on CAN-FD it could be better. So, but at this moment I have not worked on this area. But he's working. Oliver Hardkop is now part of security team of Volkswagen. So we can ask him directly. Maybe he is looking now. Maybe we can have answer on the chat. Okay, it is it is propaganda that it is steering to Ethernet, but you know, today many new processor units has up to 14 CAN channels on one device. So basically, yes, I'm not sure if that attempt to send the TCP/IP frames through the CAN is good idea or not. Maybe not. Okay. But for sure, for those small nests, around the processor, where you need many communication channels, which are deterministic, real-time, and so on, then the CAN is still maybe growing its area of application. And today, for example, I know that some companies are developing directly CAN-FD Lite-based chips. So directly something like was I2C, but I2C is not good idea for automotive because it doesn't protect the messages and so on and so on. It is good for connection of the chip on a single board, but not for anything more. But today there are attempts to use CAN-FD Lite for this area, for example, that you will have chips which are directly, which has to be cheap, they have directly finite state machine inside the chip, and they can be connected to standard CAN-FD controllers, and you have chips. Texas Instruments has now new Citara versions with 14th CAN-FD, so they probably do not think that they would not be used, you know, because if they have so many interfaces in the hardware, then
speaking of the project, when you measure latencies in different versions of the upstream kernels, my question is, what do you do when you detect a latency spike? Do you bisect the particular commit in upstream which brought the spike and later work back?
At this moment, we only do monitoring and to see what happens. We have already catch one error on the fully preemptive kernel, which has been resolved in 1 week by the people from Linutronics. It was a fast reaction, but it was hard fault basically. This.
Yeah, it would be nice if you let people know that they've introduced like a latency spike for you, because you know, like kernel is big, and in some parts people may not think about your use case, and you're already doing the testing.
Okay, this is available online, so you can test it. You can.
But the problem is, if I'm a patch sender to kernel, how would I know that you detected a spike on my patch?
Yeah, okay. So you can. Okay, at this moment at the university we do not have the. We can run maybe 10 kernel tests, builds and tests per day or something like that, and we have limited amount of the hardware, but we are in the contact with OSCDL, which has that quality assurance farm for a real time, and they plan to test our solution on their farm. So basically company which means doing the business seriously, then can ask OSCDL to run their hardware there and provide them a feedback on their development branches. Our solution is open, fully. It can be run even on different hardware than on this one. Basically, you need two reasonable CAN-FD controllers with precise timestamping. And you can run our system in-house. Okay? Okay, so thank you.
Hi, everyone. So my name is Rachel Sibley. I'm the automotive QE technical lead for the automotive program at Red Hat. And here with me is Priyanka Verma, who also works with me on the initiative. So we're going to talk to you today about how to qualify a safe Linux distribution in cars. So a little bit about the agenda. I'll talk about what is the Red Hat in-vehicle operating system and safe Linux, our overall approach to safe Linux, and how we're working towards compliance against the ISO 26262. We'll go into what is the test strategy like, freedom from interference, failure mode and effects analysis, the process aspect of it and how we're managing the requirements based on man pages, and test assets and traceability, and the work items that go into that. So what is the in-vehicle operating system? It's a smaller footprint of RHEL. We are inheriting everything from RHEL except the kernel. The kernel is the only package we're rebuilding for hardware enablement. We're using the RT kernel. It's based on OS tree, which is very common with running OS tree in embedded systems. We're working to achieve functional safety certification to conform to the ISO standard. It wasn't really made for pre-existing complex software, but there is an initiative to adapt the ISO 26262 through an ISO pass to complement that better. So we're working with a company or a partner, Exida consulting body, and they're helping us with achieving continuous certification for FUSA. So what is FUSA, or functional safety? It's the absence of unreasonable risk that could lead to harm or injury or even death later on in the road, in the vehicle. So we want to ensure that we did everything in our power to avoid potential harm to the user. So by doing that, there's compliance against this international standard. We have safety goals that are derived from potential hazards. We provide technical solutions to be able to react to these faults. A big part of it is it's very process-oriented, very rigorous, detailed flow to be able to work towards a functional safety certification. So yeah, a big aspect of it is providing the evidence so that if we get pulled into court later on or there's an audit, we have the evidence to be able to back up to say, yes, we did what we claimed that we were doing and we set out to do, and we have the evidence to back it up. So you might hear the term ASIL a lot throughout the talk. ASIL stands for Automotive Safety Integrity Levels. A being the lowest level, up through D, which is the highest level of a hazard. So ASIL A would be something like your rear light, which is very unlikely that's going to cause somebody to be in an accident and become harmed in any way, where you look at something like ASIL D, which is the airbags failing to deploy. So this is a high-level view of like the different capabilities in the car and how they would relate to the ASIL levels. For us, we're certifying against ASIL B. So ASILs are determined by 3 factors: probability of exposure, controllability by the driver, and the severity of the failure. So this slide has a lot going on, but I'll try to summarize it. So the ISO throughout the specification mentions the V model quite often. This is the verification and validation process. It's derived from the waterfall model. This isn't something we typically follow within RHEL QE. So we take what we're already doing well and complement it with the various aspects into this V model. The safety analysis is really what identifies how complex and how much rigor we really put into this. And these are the FMEA analysis, the failure modes and effects analysis, which Priyanka will get into a little bit later on. So on the left side is the verification activities where we do our system design and requirements analysis, and then on the right side we're doing our iterative testing at the unit level, integration, system level, and so forth. So for the in-vehicle OS, we're leveraging all of the same tests from RHEL. They're already doing a really good job there. We don't want to duplicate the effort there. And they also take a lot of the tests from their upstream, RHEL being our upstream, and then further upstream and so forth. So we take all of those tests and we rerun them in our environment, which is an OS tree environment. Also working on adapting the tests to a new test framework. The tests weren't really designed to work against an RPM traditional compose, so there's a little bit of work to work with an OS tree system. So because of the aspect of not being able to write and not using DNF, we're using RPM OS tree and so forth. And then there's additional work to adapt to the test framework to get them to run in our CI systems. So the requirements are derived from the ASLB APIs. So for each of these APIs, we needed to derive test cases, have targeted tests that are 100% covering the requirements, which I'll talk about in a little bit. But for where we want to be able to reuse the technologies and tooling within RHEL QE, we don't want to fork their tests, and we don't want to duplicate what they're already doing well and be able to reuse those technologies. So we have two main pipelines where we're running our tests. One is the auto toolchain CI pipeline. This is specific to automotive with building custom images and rerunning in the pipeline. And then we use where we're using Testing Farm and TMT. There were other talks about that earlier. You might have attended those. But TMT stands for Test Management Tool and highly used within RHEL QE. And then CKI is the kernel CI effort that is going on in Red Hat. They have high engagement with the upstream kernel community with testing upstream kernel trees. So they test very early in the development cycle at the patch level, and we want to be able to reuse that as well. And then the other effort is being able to provide the traceability in Polarian, which complies with the ISO standard. So for requirements testing, we have the package level verification, and this has to happen per API level. There's a very detailed workflow that goes into this, which starts with reviewing code reviews and static code analysis, structural coverage, so the code coverage analysis, the requirements level verification, which is derived from the man page of the API. We then take an API we take a man page and we break it down into low-level requirements. So we are able to break that down into something more that's maybe something that's ambiguous. We break it down into testable parts to ensure that we have the traceability for all the behaviors that are specified in the man page. And then if we find any discrepancies with the man page, it's also a chance for us to be able to file a merge request to be able to provide those changes to make sure that the specification, e.g. man page, is actually doing what the implementation is designed for. So the integration level testing, this comes out of the safety analysis, which I mentioned earlier. So the failure modes, effects and analysis, where there are specific failure modes that are identified within an API and external syscalls and dependencies, and we need to ensure that our existing package level testing is already covering the integration level testing as well. And then again, more details about putting that into Polarian, adding the requirements. We need to have the requirements linked to test cases and test cases to test runs and so forth. So Priyanka will talk about that a little bit. So I talked about code coverage analysis earlier. So the ISO recommends the software is verified using code coverage analysis. The target is 100% compliance for the recommended quality metrics defined in the specification. We don't have to do this for every API, only for the complex APIs. We also use it to assist us with the simple APIs to ensure that we have the 100% requirements coverage. So within the specification, you'll see recommended, highly recommended for all of the techniques within the V model. So for the code coverage, structural coverage, it's recommending both statement and branch coverage. And so for code coverage workflows, we're trying to do more granular reports that are specific to the API level, rather than running against the entire package source, be able to do detailed analysis where we can drill down into specific API to see where our gaps are. So the low-level requirements also have code coverage analysis that are showing the traceability of the tests to the requirements and the test coverage there, so that helps us understand where are gaps with code coverage and requirements, and therefore requirements coverage, to know, well, I need to go and develop new tests and then push them upstream to be able to pull them back down to RHEL.
So another major aspect of functional safety for road vehicles is freedom from interference. Freedom from interference is about absence of cascading failures. As we can see in the image, the cascading failure is the failure that actually cascades from one element to another. So for example, there was an event that causes a fault in element A, which made the element A fail. And the failure of element A causes the fault in element B, and it fails the element B. So this is a cascading failure. So freedom from interference is majorly about avoiding the cascading failures. So it's also linked to the ASIL, that is, there should be freedom from interference between lower and higher ASILs, or a quality managed level to any ASIL A, B, C, or D. So how do we ensure freedom from interference? First thing, we analyze. So there is DFA, dependent failure analysis. So this covers the cascading failures, which are for the freedom from interference, and then also the common cause failures, which are related to the independence. So common cause failure, as the name suggests, it is due to a common cause that at the same time fails element A and element B. So these failure analysis help us, figure out the failure modes that could lead to the failures, and we try to mitigate those failures. Again, these dependent failure analysis are of two categories. One is deductive analysis, and the another one is inductive analysis. So as Rachel mentioned, that we are targeting ASIL B. So according to the functional safety standard for road vehicles, for ASIL B, it's highly recommended to do inductive analysis, which is FMEA, failure mode and effect analysis. So under this exercise, what we do is we brainstorm and list the failure modes that could be applicable to a particular component, and then further analysis happens where we calculate the risk priority number. So risk priority number is nothing but the multiplication of severity, occurrence, and detectability. So we get that number after the multiplication, and then we have the data for the failure mode. Now comes the chance of mitigating that failure. So we apply technical solutions to mitigate the failure that we have already listed in the FMEA. So after putting that mitigation, again the risk priority number is calculated, and it's checked if it is if it's under the acceptable range or not. And from the mitigations, then finally there is one more way of deriving requirements, that is through failure modes, that comes into picture. Now comes the process aspect. So process aspect is majorly about the evidence and then the traceability. So evidence is that we have to prove that we did what we were supposed to do according to the functional safety standard. We have to prove that we tested a requirement, or we made sure the failure mode was covered with the mitigations, and we followed all the timelines, the fault time tolerance interval, and a lot of more things. So these evidences could be for testing, for QE, it could be our test asset, it could be our test plan, our test specification, and our test reports that tell us when we tested the requirement, how we tested the requirement, what techniques were used, and what methods were used, and what were the results, which tools we used. So we have all the data if we want to retrieve. And along with all the data, this data needs to be traceable. So we should be able to make out which test is for which requirement and which result is for which requirement, whether the failure mode has the right requirement associated to it, or was it tested well, was it 100% tested or partially tested. So that kind of data should be traceable. So yeah, that's traceability is one of the things that add value to the evidence, and evidence which is not traceable is not valuable. So how do we achieve it? We are doing it by using Polarian. We are using Polarian in different ways, as you can see, for our test case management, for writing our technical safety concept, managing our requirements, and something that's in progress is the configuration management, tracking our change requests, whether they are related to the tools, the process, or the requirements. And lastly, we are using it for the metric reports, like the traceability metrics, and also the pass-fail metrics according to the requirement. Now we come into how do we derive the low-level requirements and the associated conditions of use. So as Rachel previously said, that we are taking reference from the man pages of the associated APIs that are in the safety scope. So first we analyze the man page, and from that man page we derive the low-level requirements that are testable. And now there are other things that come into picture that are assumptions or the conditions of use. These assumptions of use or conditions of use come into picture when the fulfillment of these low-level safety requirements is dependent on the context. For example, I define a requirement for an API, but that holds true only if my system is 64-bit. So that is going to be my assumption of use, that the so-and-so requirement should be verified and it passes because if you use the right environment. So that's the assumptions or conditions of use. Later, yes, the verification happens, and yeah, that's how we move forward. Next thing, when we talk about man pages for deriving requirements, the first thought that comes into mind is man pages are subject to change because they're upstream, right? So how do we detect and handle those changes? So we have an application that runs and gives us the diff if there is a change, and then there is a CI that's automatically triggered and MR is raised. And there the analysis happens which tells us that whether the change is related to the API in our safety scope or not. If it's not in our safety scope, it automatically gets merged. And if it is in our safety, if not in safety scope, it's automatically merged. And if it's in safety scope, then the MR is pending for review. So what happens when there is an MR pending to review due to a change? Then our change management workflow comes into picture. A change request is opened, and then the impact analysis takes place. In that impact analysis, we take into account the technical impact, the schedule impact, and what are the different work products that will be impacted due to this change, whether it affects only documentation or testing development and documentation. So that kind of impact analysis is performed. Based on that impact analysis, there's a change control board that approves or rejects a change. So once the board approves the change of the man page, the related requirement gets the change of text, and hence the implementation changes, and hence followed by the V&V activities, that is validation and verification activities. Now, the traceability aspect, how does it fit in the complete scenario? So we have low-level safety requirements, we have failure modes, we have man page-based requirements. And for traceability needs, according to the functional safety standard, we need to have bidirectional traceability between the different hierarchical levels of the requirement. For example, if I'm at the lower level requirement, I should be able to trace back to the top level or the parent requirement, and from there I should be able to come back to the related or derived low-level requirement. And hence, the requirement should also be traceable with the test specifications that are verifying that requirement, the test results, and hence the test plans and test report. Basically all of our test assets. And same goes for the failure modes. So our failure modes should also be traceable according to what test plan they were planned in and the test specification, reports, and more. So this is an example traceability report, how it finally looks like. So what you see here at the top level is the man page-based requirement, and which is further associated to the low-level requirements that it has, the failure modes, that are in the blue icon over there, and that exclamation mark is for the assumptions or conditions of use. And below that, if you see, there is the low-level requirement associated with the test case. So we see that which test case is verifying which requirement and how the requirements are, related to or bidirectionally traceable to the failure modes. So that's an example. Any questions? Yes, please.
Does the standard, it applies to failure modes in software only, or it can apply to failure modes that software can cause in hardware?
Yes, actually the standard incorporates it is for all three levels, at the software level, the hardware, and the system level, which is software plus hardware. So currently here we are concentrating on the software part for now, and maybe in future if it this life cycle permits, then yeah, hardware and software interfacing HSI. Yes, please.
Which tool are you using for the coverage analysis? Is that like GCov or Fidelity?
Yeah, GCov. Yep, and GCov-R as well. The question was which tool were you using for code coverage analysis? GCov, GCov-R. Yeah. Yes.
Are you going to contribute to tests that are developing to increase coverage to the different projects? Or?
Yeah, a lot of the work that we're doing for the safety scope, like a big part of it is affecting glibc package, for example. So there's a very large upstream test suite that we're rerunning for Rivos, and then we're trying to break it apart by the unit level to show the traceability to the specific failure mode or the specific package level test against the API. So new tests are being developed and they're being staged, and we're in coordination with the SMEs about how to be able to upstream those tests to the glibc project, because then RHEL QE can take advantage of that and then pull them back down and rerun them for RHEL as well.
Can you elaborate a little bit more on how you come from like high-level requirements, like when you start with like brake light doesn't work, rear view camera doesn't turn on, to a very low level stuff like get end, like why get end, right?
The question was how we create this requirement hierarchy with the high-level requirements with the man page and then low-level. So there's even more levels actually beyond that. There's the technical software safety requirements that are defined from our safety goals, and then they trickle down to our man page requirements, which go to the API like getenv, and then from the API getenv, we then look at the man page, and then we look at the behaviors within the man page and then break it down into functional parts, because not every part of the man page is something that you would test, for example. So those become low-level requirements, and then those get fed into code coverage analysis to show that we have 100% code coverage against those low-level requirements. But now we might not always get 100% code coverage. So as long as we can provide justification as to why that code path wasn't reached, for example, that's allowed. But otherwise, for the complex APIs, we have to have 100% code coverage.
Do I understand correctly that you also work with those who are going to actually write the application for the operating system, right? Like, the operating system doesn't turn on the brake light. There's going to be some application from someone who does that, or like a rear view application, and you take the requirements from them, basically the list of APIs they're going to use in the operating system, and then these become your like safety.
Yeah, where do we get our requirements from? The APIs, which are our ASIL-B APIs, those come from the OEM. So they provide the list of APIs within the safety scope. Of course, we work with them to influence them and help them guide them about which ones should be in the safety scope. But those specifically, yeah, come from our customer, which is GM, who we're working with right now. So the question was, some of the man pages are very minimum, and then they point to other documentation. Was that the question? We will have to handle that, yes. There's syscall wrappers and that sort of thing. So yeah, that's something that we need to handle, and so part of it will be redirected back to the actual API that's wrapping around it. So there's different use cases based on if it's like a syscall wrapper or the API, or and then there's different categories of very complex, high, medium, low, and there's different rigor that's taken upon the complexity of the API as well. But eventually those are going to be broken down into two aspects, simple and complex, once we get to a point where we can do that classification. All right, well, thank you very much.
Please come in front, especially if you will have questions, because yesterday, I couldn't hear anything from the audience. And in the last 3 rows, nobody could hear anything as well because of the air conditioning. I mean, feel free to stay there and do something other work, but if you want to listen to me, it's going to be easier from the front. Thanks. Still have 1 minute, so. Oh. Okay. So, hello everyone. Obviously, my name is not Barbara Bunova. I'm a last-minute jump-in because there was an accident. There was an argument between Bara and the staircase here at the conference, and she couldn't make it today. So my name is David Hallis, and I would be talking about trust management in digital ecosystems. Hi. Please try to sit in the first rows because in the back you cannot hear anything. Ciao. Stay in the front so you can hear, unlike yesterday. Okay, so I'm going to stay seated because first of all, I'm tired. Second, I have some notes from my supervisor who actually prepared this talk, and I'm just the last-minute replacement. So at the beginning, I would like to talk about our university, which is not this one, but the other one. It was established in 1919. It's the second largest in Czech Republic after Charles University in Prague. It has over 30,000 students. Our youngest faculty is the Faculty of Informatics, which has over 2,000 students. Bara is the Vice Dean of Industrial Partnerships, so I guess that's the reason why she had the slides there. So, as digitalization is advancing and getting more and more normal in our lives, there are new challenges that we have to tackle. And also there is the dual-use dilemma that technology can be also used for good or bad. And if we want to embrace the good, we actually have to use it. Banning it is a bad idea. It's the same as with fire. You can use it for good and also for bad. And if we talk about digitalization, there are challenges regarding hyperconnection. So every device will be talking to every device. Humans will have more interactions with machines, which brings us to the topic of dynamic, autonomous, and not just autonomous, but dynamic cyber-physical ecosystems, where uncertainty and unpredictable situations can happen on a larger scale than before. And obviously we have to secure and future-proof these technologies so we can catch issues that can happen that we don't even know about right now. So our research specifically is around critical infrastructure, which makes it critical because it's usually human lives are at stake, or the way of our life is at stake. So we talk about smart grids, autonomous vehicles, smart cities. It's basically everything that's around us that can harm us if it's used in a bad way. I mean, that's our view. There are different definitions of what a critical infrastructure is. So we believe that trust might be the way out of this, the way how systems trust or not trust each other, or even humans, or system trusting humans, human trusting systems. So our first view on this is the trust management in an Internet of Vehicles or a network of vehicles or vehicle area networks. We can talk about collision avoidance. So if two vehicles meet, then may vehicle A can trust vehicle B if they behave to avoid each other from colliding. Then there is vehicle platooning. When you have, as you see on the picture, multiple vehicles, we can move them into one lane, and the aerodynamic resistance gets lower except for the first vehicle, so they can save fuel, for example. Can the randomly joining vehicle trust the other members of the platoon, or can the platoon trust the vehicle that's trying to join the network? Then there is my research, kinda, the runtime update, or running smart agents in the vehicle and trying to assess some kind of trust against that software that's being run. And of course, as I said, it's the human to autonomous vehicle trust. Let's say there is a human that's driving a vehicle that starts becoming autonomous slowly. I'm not talking about like hours, but like in weeks or months. So a human starts driving the car, but the car is slowly taking over as the human allows it. So we can have situations like this, where we have traffic lights still, which wouldn't be needed in a fully autonomous system because only for pedestrians. So if we look at how trust and trustworthiness was handled by the industry before, increasing the security or reliability or availability of these services, these technologies, doesn't really improve the trust itself in the system. It's not a conventional problem in computer science, because trust, as we interpret it, is a human or social concept, a belief that the other system will not do harm to you by exposing vulnerabilities to it. And even though the system might say that, hey, I'm trustworthy, it still can, and it's certified and everything's fine by some checks in the past, it can behave bad in the future. And we can even intentionally design devices that would have one sole purpose of do harm and do damage at a certain point in an ecosystem. Let's imagine a vehicle that behaves well for 14 days, and on the 15th day it will just do something that would collapse the whole city and kill a lot of people. So that's what I was talking about, the agents with malicious intentions. Banning this, which sometimes comes up in legislation, isn't really a solution, because somebody else will anyway implement it. That's one of the reasons. So we need to be proactive and come up with technologies that will solve these problems. Again, so understanding trust, we started doing some surveys about, in other fields of science than computer science, about what trust is, and we found these nice definitions. So basically, trust is a relationship between a truster and a trustee. I mean, if you want to read these, I can give you some time. But what we got into is the trust in automation definition that suits mostly our needs, which is basically a belief, a relationship between the truster and the trustee in the context of uncertainty and vulnerability, to expose some kind of side of the truster that the trustee could exploit, but in a safe environment it shouldn't happen. So this kind of trust is subjective. So if A is trusting B, it's not necessarily true that B will trust A, which is also asymmetry. And transitive. So if agent A is trusting B, then and B is trusting C, then A might trust C as well, but not always. And we can go into like reputation and how like social structures let's say, humans gossip about each other or have reputation about each other. So let's say one person is very famous and they talk about him, and you hear good things about him or her. You hear good things about that person, then you might trust that person implicitly. So we can evaluate trust in various scopes. So there is a local in a situation locally, like two vehicles meet, then they can assess trust. Then, based on that relationship in the future, they can build up some kind of reputation that can be consumed by other consumers of this trust framework. And of course, it can be context specific, that you can trust a vehicle in a collision avoidance scenario, but for example, you cannot trust it in a vehicle platooning scenario, for example, because of a faulty component or a wrong implementation. So we are looking into some kind of dynamic evaluation where we deal with these things. So we came up with this nice picture of how is trust. Guys, if you go to the back, you will not hear much. So basically, we have direct and indirect trust. Direct is when you interact with some other entity directly. Indirect is if you hear some kind, again, gossip, if we talk about humans, then there is some kind of context information about the specific situation, and based on that we can aggregate these results and make a decision about trust, which in our case, as I stated yesterday, if you have been on my talk, should be probably non-binary, some kind of complex structure. We don't really know yet what, but so far we work with percentages in some kind of proof of concept case studies, but it will probably like a vector of different percentages. So if we evaluate trust directly, we don't talk about reputation, but just trust only, then there is a quality of service metrics when we talk about reliability, availability, or accuracy, and there is the social metrics when we talk about these human aspects of friendship, honesty, benevolence, altruism, or unselfishness, and we need some kind of ways to measure these. So, two metrics we already know how to measure. There is openness or transparency, and our view on this that we could use digital twins. Is anybody familiar with digital twins here? Okay, the ones who were on my talk yesterday. So a digital twin is a model of a cyber physical system, but only existing in the cyber world. So you can use it to simulate what this actual system would do in the future if you put it into some certain context. And if the cyber physical system shares with you this model, it means some kind of transparency, like, hey, I'm willing to give you my model, I'm open about it, you can use it to determine my future moves. So this is our way of defining openness in certain cyber physical situations. The other one is honesty, is how good this model is, how honest this model is. Basically, if you run this model, it behaves in a certain way, but the vehicle doesn't behave in the same way, then we can assume that the vehicle wasn't really honest about this digital twin. Again, we have these challenges that we are trying to solve. There is a thing-to-thing update trust. So the vehicle is trying to download some kind of upgrade, a black box, and can we trust it? Can we run it? Can we expose it to critical functions of the vehicle, or will it kill us? Then there is thing-to-thing trust, when you have two entities trying to assess each other's trustworthiness, how much they can interact, how much of their safety features can they turn off to be more efficient. Usually if we talk about safety features limiting vehicles, let's say slowing them down. If you trust another vehicle, you will probably pass each other with a higher speed because you trust it and you don't feel that much vulnerable. But If that trust level is lower, then you probably do it in a slower way when you have more time to do sudden reactions if there is something bad happens. Then there is my research about adaptive safety, that how much should we impose these safety features directly based on the level of trust or the trust score, and what happens if I do a false positive and false negative assumption, which one of the partial solutions is that, as I said, the non-binary, the percentage where you have much lower chance of false positives and false negatives, because you don't just have the two extremes. But we'll probably take it more to some kind of vector, which is still in progress. And the last one is governance, that who should be responsible for keeping up such ecosystems, who should be managing the trust from a centralized way, who should be responsible for certain things, and of course we also look into the ethical side. So regarding things to think update trust, one of the scenarios is what I was talking about, is a digital twin being ran, let's say a software module that ensures in a smart city speed limits or certain traffic rules, how we ensure that this third-party software will not break our vehicle and also do its purpose, limiting you in school zones, let's say. We treat it as a black box. We simulate its digital twin and do predictive simulations, and based on those predictive simulations we can do the live compliance checking, assess its how much we can trust it, and based on that expose it to certain features or not. Or if it's really bad, then we can trigger some kind of safety system that disables it and doesn't allow it to run the agent in the vehicle at all. This is the architecture I was talking about yesterday, so I'm not going to go into the details about it, but this is supposed to somehow enforce a software module to run in a secure way on autonomous vehicles. And the next one is collision avoidance. We have some experiments with drones that assess trustworthiness of drones based on previous behavior, and also pull in reputation into the picture and try to avoid collision in mid-air. Then there is adaptive safety, my research, where we are trying to adapt safety features based on the level of trust and safeguarding how vehicles will behave in an uncertain and unpredictable world. Not just vehicles, but we are trying to demo it on autonomous vehicles, most of the things. Again, this architecture that I'm not going to go into details with. We also designed some kind of adaptive safety framework where you have a model that calculates you a trust score or value. We propagate it to the outside world. There is a safety module that, based on a decision tree, turns on some kind of safety features or exposes some features based on how the trust is changing over time. And there is governance at the end, where we are looking into how to actually calculate the trust, how to represent it, how to punish or reward systems that are breaking or increasing their trust, what kind of attacks are there, and also we are looking into evidence collection, some kind of forensic readiness that we can give it to legal institutions later if there is some kind of misbehavior, because that might happen. There's also pre and post incident. Then there are problems that we haven't solved yet, like what kind of trust score should we assess to newly joining, let's say, vehicles or entities to our system. Then we will probably need some kind of erosion or inflation on the trust score, because you might have been trustworthy yesterday, but it's not necessary that you will be trusted today. And there are some kind of attacks like black swan blindness and other sources that we are looking into it also. So the challenges are The scope is situational. So in one, as I said earlier, in one scenario you can trust a vehicle for, let's say, lane keeping, but in another one for speed control you cannot. That trust is subjective. Again, the default trust score, as I talked about, and erosion. We also need to figure out how to detect malicious intentions that are hidden. So let's say 14 days system is doing well, increases its trust score, then on the 15th day it just goes on a rampage and starts killing people. How to ensure safety against untrusted agents, like cyber physical system can limit the cyber part, like vehicles, you can disconnect them from the network, but it will be still in your smart city, it can do still damage. So we probably need some kind of means to enforce our rules, like police will be not jobless at that point. And there is also still a high degree of dynamism and uncertainty. We will never know in the future how will be the convergence of a network of, let's say, autonomous vehicles or any kind of smart systems, because they will change over time and you will have millions of unpredictable combinations. So regarding attacks, one of my colleagues is looking into what kind of attacks can happen. The important part is there are individual and collusion attacks, and usually they can end up either in unreliable decision making, so we have some wrong trust evaluation, and based on that we do something that we shouldn't do. And the other one is false trust recommendation, when we have too high or too low rating and recommend to another system that can do bad things. Some of these attacks are like self-promoting, when the system is trying to say good stuff about itself. Then there is whitewashing, when probably you've done it in your childhood, that you created an email address, you did something on the internet, you got banned, and then you created another email address and tried it again. There is discriminatory attack, when it tries to attack other actors of the system and tries to pull down their trust score. And there are other things like on-off attacks, when it's sometimes good, sometimes bad. We need some kind of system that can handle these kind of situations. Then there is bad-mouthing, when I can bring up like from human social situations in primary school, when 5 kids are starting to pick on one kid and start saying bad things about that kid. This can happen with autonomous vehicles. Or the other thing, the ballot stuffing, that 5 kids will agree that one of them will have a high, or 5 vehicles will agree that one of them will have a high trust score by trying to prove that it's doing good and good and good, and at some point on the 15th day it will start going on a rampage. So this is the things we are working on, 4 different aspects of this thing. Mine is more the adaptive safety and the architecture around software modules, so that's the thing I can take questions to. The rest of them I can try. Thank you. Any questions? Yes?
So decision tree.
I cannot hear you. Please come closer or shout.
I will shout instead. Okay, so that decision tree you were showing, is that trained continually, or is it frozen and just applied? Yeah, this one. Yeah.
Do you need a one-word answer?
Yeah, exactly. Because I'm wondering, like, if you train it on something, you know, before you deploy this thing, you let it frozen, or if you had it trained continually on new data, you know, because these things, like, they can change over time, you know. So I'm wondering about that. That's the first part of my question. The second question is, how exactly is that decision tree designed? I mean, what kind of algorithm do you use for that?
Yeah, so I have to repeat the question. So the first question was if this decision tree is static or dynamic, and the second one is how it is designed. It will be probably dynamic. Not sure how much dynamic, I cannot answer you it right now, but in uncertain situations you cannot have a static one. It might happen that vehicles will exchange their decision trees at some point. We are also looking into that, but we are not really deep in it. And how it will be designed, that's also an open question.
Thank you.
Anybody else? Please. Okay. Do we have any questions on Matrix? Do we have the session chair? Okay, if we have no session chair, then I guess this was all. Thank you, everybody, for coming. See you at the party.